like people who can't afford, who say they can't afford to live, which is really they just want to do what they want to do without working. They go and post up next to where it's easy to get free stuff, and that's just where then it's like, oh, it's a crime-ridden city. You just got to get rid of these
Well,
vagrants or
speaking
whatever.
of free stuff and crime-ridden
exactly.
cities, we're about to enter the Celestial Theodolite event here. If you guys want to take a minute to wrap up your whatever you guys are talking about for a second before we interrupt.
You're
Oh,
not the boss of me,
I
Shane.
think
What should we do, Shane?
yeah,
You're the
I think
boss.
we're good.
Is that an American theodolite?
Fantastic. Yes, it is. All right, cool. Let me do the intro real quick. I'll be back in less than 30 seconds, and then we will beginneth the presentation.
Just want to say thank you for indulging us, Canadian.
No worries. I'm going to go ahead and Pure Rigor, if you mind turning that whatever you're doing off, please. Thank you.
No thanks.
Yeah, you Canadians are right. If Russia came over and started picking a fight, we'd back you up.
Oh, thanks, bud. We appreciate it, eh?
I'm no northern apologist. Just kidding.
I think I find that offensive.
Okay. I like how Minnesota is just like almost Canadian.
Is that what that was supposed to be?
We don't. Canadian.
They're almost Canadian.
It's good to laugh at each other once in a while. So, kudos to all.
Absolutely. I was just trying to do an impersonation of you earlier. Listen, buddy, you think you can imitate me?
That was actually not bad.
Pretty good.
Yeah. Nice.
You should see Q Up. They did a whole skit on me, apparently.
All right. Hello and welcome, everyone, to Celestial Theodolite update number 24. Today, we're going to be going back to the basics and kind of give a top-down overview and walkthrough of the process, the mechanics of how it works, and the basic fundamentals of it, so that it can be understood. So that before we get to talking about the data and the measurements, etc., we actually have an understanding of what's being put forward in the first place and how we are using the Celestial Theodolite to externally test an internally consistent model. So I think tonight we're going to be joined by Coco and one other, if we can get a Flat Earth lad to join as well. So we can do, we're going to play a game of Do You Agree? And we're just going to kind of go through units of measurement, how the sky is divided up, how fast it moves, etc., and just kind of set the baseline for what we're working with, so that we can understand, what the data, what the end product of that was. So if we have any Flat Earth lads that want to play, Do You Agree? Volunteer now.
I volunteer as tribute.
Was that Hasbro PSYOP? I saw your mic go off. Did you say something?
That was me.
You in? You in it to win it, my dude?
I'm in it to win it, bro. I got free time for the next couple hours. Let's get it. I love your presentations, by the way, bro. Thank you.
TY. All right, Coco, are you there, lass?
I am here.
Fantastic. Okay, we'll go ahead and start the game in a minute. But before, I have a quick announcement to make. There has been a lack of celestial theodolite measurements as of late. The weather, people have been busy, etc., etc. So we put together a little slush fund from the Ether Cause lads. And what we're going to be doing is, if you live in the southern hemisphere, you can do some celestial theodolite measurements and submit them. You will be paid $50 per mountain peak that you record. Now, you don't get paid per star or whatever. You can use the same peak at different distances if you want, multiple payments or whatever. But yeah, that's what we're putting out, a bounty for celestial theodolite measurements. So a quick recap of what you need to do to participate. All you need to do is go to wherever the location is you're going to be shooting from. If you can get a daytime picture of the location, that would be awesome. So we can, in case we need to do comparisons and tracking down the stars and whatnot. But the most important thing you need to do is write down your latitude and longitude of where you're recording from, and then identify the peak that you're shooting. So you can use an app like Peak Finder. It has a large database in it of all the peaks around the world. And when you overlay it and look through your phone, it'll tell you what peak you're looking at. So just give us that peak name and give us your lat long that you started the recording from. And then on top of that, but there's one final hurdle to overcome. We need the exact timestamp of when you started the video, and we need your frame rate. And if you can sync your recording time to GPS time, that would be fantastic. That would make it super easy. So that's all we need is your lat long, the mountain that you're shooting, the name of it will suffice. We can do everything else on the back end, and then just give us your recording information. So if it's, I think we can probably figure out the frames per second too if we had to. So really, we just need the time synchronized to GPS time. So if you have timestamps that you can put in the recording, or if the file name that's created when you start the video or whatever puts the epoch of when you started it, that's all you need to do, and you can collect your $50. So how to collect the $50?
Alan, you wouldn't
Yes.
happen to have that Bluetooth thing still on, would you? Because you got some weird interference coming on a little bit. Maybe it's just me.
Did anyone else hear anything?
I didn't hear anything. Nothing that I know.
I heard it. I know what you're talking about. I heard what you're talking about.
Okay.
I definitely heard something. It sounded like someone was like on a seesaw in the background or something.
Yeah, it was like a high pitched whistle or whatever. I felt like if you're using your Bluetooth thing before that was super annoying, that might still be connected. That's what I was hoping it was.
From death metal, my ears can't perceive that.
All right, inshallah, it's off.
There we go.
But, all right, yeah, thank you. I didn't realize I was on. Okay, so how to collect the money? My email address is alan_audits@gmail.com. That's ALAN _audits, all one word, no underscores or anything, @gmail.com. Just send me an email of where I can download the files and whatnot, in your PayPal or your Cash App, and we will send you the $50. So that goes for Southern Hemi lads. And then also, if you live in the Northern Hemisphere, if you live at sea level or 200 meters above sea level, you're also eligible. So we need some sea level measurements, and different angles and stuff would be nice. So whatever you can come up with, if you live in the Northern Hemi, if you want to record some stars, get $50. You get $50 per peak. So that's the offer on the table that will add to the data set. And then I'll make a more formal written out thing here in a bit, and you guys can reference that or whatever. But yeah, we are looking for people to participate in the measurements. Okay, so now that that's out of the way, I think we're ready to begin on the celestial theodolite. So Coco and Hasbarap? What's your name?
That's Noah.
Noah. Okay, I thought so. Noah. Okay, Coco and Noah. Okay, so this is a game of Do You Agree? This is how the sky has been divided up into 360 degrees, and you can also reference your appendages to get some rough angle measurements. So if you were to hold your finger up to the sky, the width that your finger takes up would be 1 degree. If you hold up 3 fingers, it's 5 degrees. A closed fist makes 10 degrees. Index and pinky out make 15. Index and thumb, pinky and thumb come out to be 25 degrees. Does everything make sense so far?
Yes.
Yeah, that's pretty cool. I did not know that.
Yeah, that's pretty awesome. And then another way to conceptualize this is they actually take smaller measurements that are called arc seconds and arc minutes. So you can actually take this 1 degree here. So if you take your thumb and hold it up to the sky and imagine that you have 60 sheets of construction paper, and you could arrange them such that they're not touching, but they're just equally dividing up your finger, you can divide that 1 degree up into 60 minutes. 60 minutes equals 1 degree. Now that's a thick piece of construction paper to make the arc minutes, but you can also break a minute down into 60 seconds because there's 60 seconds in a minute. So imagine you had even thinner sheets of paper, just like regular plain paper, and you could divide those up in between the ones that you did for the minute, and then then in between those you'll have 60 sections for 60 seconds to equal a minute. Does that make sense?
Yeah.
Yes, it does.
Awesome. Okay, cool. So if we hold our fingers out, index to pinky, we can make a nice 15 degrees, right? So if you hold it up at the sky and you imagine a star at your index finger, 1 hour later, it'll be at your pinky finger. If you were to hold your hand up for an hour in that same spot. Make sense?
That's pretty cool. Yeah, it does.
Yep.
Awesome. Okay, so we already went over the breaking down of the minutes and seconds using the paper analogy, but here's what it looks like in math form. So 1 degree is equal to 60 minutes. 1 degree is 60 minutes, and then you could break 60 minutes into another 60 seconds. So you can break 360 degrees into 3,600th of a second. And it's just basically, if you'll notice here, that's just an extra zero on a 360. So it's just kind of, that's the interval of how it extends. And then when you get into, we're not going to get into it here, but they have micro arcs and milli arcs, I think, which just extend that out. So they get down to 3,600,000th of a degree and then 3,600,000,000th of a degree. But for the stuff that we're going to be talking about here, it'll just be down in the arc minutes mostly. And we might round up some arc seconds if it comes close to an arc minute. Okay. So because we know that this will return back in 15 degrees per hour makes 360, we know how fast it can go. So we can do the linear velocity equation. We know that this will return back in 15 degrees per hour makes 360. We know how fast it can go. So we can do the linear velocity equation and determine exactly how fast the positions of the stars are moving over the Earth. Now, whether or not the Earth is a globe or flat or stationary or what have you, like a geocentric view, either way you slice it, the ground positions of these stars to complete that 360 at 15 degrees per hour can be made into a linear velocity. So if you have the circumference of Earth and that 24-hour period in seconds, you can do velocity equals circumference divided by time. So that's just distance over time. And that will give you 486 meters per second. So that's how fast the stars are moving over top of us at the equator, I believe. I think I have that added on the spreadsheet. So does that make sense so far? Like the rate of movement is proportional to these angles over time?
Makes sense to me.
I'm sorry, 464 meters. I might have said that backwards there.
Can you just re-say that real quick for me?
Yeah. So we started with angles and time, but because we have the circumference of Earth, so we have like a distance for them to travel that 360 to complete it, we could take the full completion of that circle, which is the circumference. So we could take 40,075 kilometers and do over 86,400 seconds. That's how many seconds are in 24 hours. So we could just take how long it would take.
I have a question. As per the circumference or whatever, wouldn't a glober just claim the circumference is different? Like the equator is the maximum circumference, and then as you go north or south, you get smaller and smaller circles.
Yes, absolutely. You can actually do the cosine of wherever the latitude is, and that'll give you the linear velocity at that location. So actually on the spreadsheet here, we have we'll start with, I'll just show you real quick. At Pikes Peak, Colorado, I think the latitude was like 38 here. So if we look at the equator reference in imperial units, we have distance at the equator is 1,038 miles an hour, or 1,522 feet per second. And then if you go to if you do the cosine of the latitude, you'll get 1,185 feet per second. So that'll be the rate of change for that. But yeah, it all equals out to what it would be based off of the circumference at the equator either way. Because it's still completing the same circuit. Yep. All right, Coco, are you good on the distance over time conversion to get how fast the stars move over the ground in terms of if you were to get your speedometer out and clock them?
So you had almost gotten to that part when Noah asked his question.
No worries. Okay. So distance over time we have the circumference of Earth. That's how, like, if you were to hold your finger up and that star was directly above you, like just looking straight up 90 degrees, it will take, it's going to traverse 40,075 kilometers, and that's going to take 80,000 or 86,400 seconds. So we could just do circumference divided by time, and we can get how, like, that linear speed per second.
Right. So I'm going to give you that's how you get that. I'm going to tell you ahead of time, though, that I'm not really going to remember that calculation.
Oh, that's perfectly fine. It's just it's basically like if you're familiar with, like, they say, the Earth rotates at 1,000 miles per hour at the equator or whatever it is roughly. This is how they determine that. Basically, it's just like, long story short, this is how they came up with that.
We're trying to get to the conclusion that the angle determines time, so we're going to establish each independently and then put them together.
Yes, because the globe model, celestial navigation, etc., as done with the celestial sphere model, is predicated on angles equaling time and vice versa. So if you know what time it is, you know the angle to the star. If you know where that star is at, based on its angle, you know what time it is.
But doesn't the objects move at a different angular speed depending on what, like how far off the ground, how far from the horizon they are? Like, don't they move slower at the center of the sky versus faster at the equator or something? At the horizon, something like that?
No, that's a really good point. So going from your zenith to about 20 degrees, or probably 10 degrees, they travel at 15 degrees per hour. And then as it gets at those lower angles, there's a lingering or looming effect. Now, this could either be due to optical circumstances of our nonlinear vision, or it could be in a combination of refraction, or it could be solely due to, refraction as the globe mainstream asserts with astronomical refraction. But yeah, when it gets lower in the horizon, it doesn't follow that 15 degree per hour relationship anymore. But to keep and to explain why they're still visible at those locations and not following that 15 degrees per hour, they just invoke whatever astronomical refraction would be required to keep the star at that angle, so that it maintains usefulness for its ground position.
I almost feel like that's somehow fallacious for the globe to kind of, like, they're asserting, like, go ahead.
Yeah, no, I kind of felt the same way, but kind of think about it like this. The only thing that actually follows the 15 degrees per hour is called the true position of the star, which is this. Just if you were to view a star transiting over your head at 90 degrees, and you were to take a snapshot of like the time that it was there, it would come back exactly at 15 degrees per hour, but only in that band of, being directly above you. And what they do is they project out that true position. So, like, they take that snapshot from that original zenith measurement, and then they just go, okay, that's moving at 15 degrees per hour. But then they separate that position, that calculated math source position, from the apparent position. So as you get to different angles, they're like, oh, it's actually refracted up. So you're no longer seeing that almost 1-to-1 position of the star from when it was at your zenith. You're seeing an apparent image of it. And then as it gets lower, they're like, oh, the apparent image is separated from the true. But the light source true position does follow the 15 degrees per hour, but the apparent position does not.
I understand.
Awesome. All right, Coco, making sense so far? Still good on that?
So far, I think I'm following it. Thank you.
Awesome. And then just real quick to reiterate on the true positions and stuff, right? It starts off as just, hey, I'm looking up 90 degrees above me and there's a star. And then how long does it take to come back? And it came out to be 15 degrees per hour. But if you apply that same 15 degrees per hour to the optical star that that same star that you're seeing as it gets lower, it doesn't follow that rate. So to come up with the difference between the two, they just say it's refracted a bunch.
The difference between the two, they just.
Okay, and then we're
I understand what they're saying. I don't know if I agree with it, but I do conceptually understand it. So I'm just going to go with yes.
Yeah, awesome. Yeah, the conceptual understanding part is super important because we're actually going to use the principles of the light source is movement versus the apparent motion that we see from what we see in the sky as part of the occlusion process. And then as it's going to turn out, the true positions when they intersect with physical objects, we're no longer able to see the star, which gives some indication to the way that I kind of conceptualize it is that there's a true source star somewhere. We don't know where it's at, but what we see is always the apparent thing. We never see like the actual source of it. And like if you were underwater looking up at the sun, and you know how it's like displaced in the water, like that's kind of what we're looking at. We never see the true thing, but we can reference it. You know what I mean?
You
Like
see, I would agree with you. And I believe like that description you gave earlier of the non like truth, like that's also the Glober. I think even the Globers agree, dude. We all agree we're looking at an apparent position. Well, the honest Globers all agree that we're looking at.
Even in their model, it's apparent in both the sun, the moon, all celestial bodies are apparent. Sorry, was there a question? I thought I heard someone.
Yeah, Alan, it's Shalom. Just letting you know that your audio for you is great on YouTube, but the participating audience on Discord is super low. I don't know if you could do anything about that.
So I also have a question when you get a second.
Yeah, go ahead. You're good. I think I fixed the audio. Should be good.
Okay. So I don't really know anything about astronomy or anything else. So I always just thought when I was looking up at the sky, I was looking at the light coming from that actual star or planet and stuff. But you're saying that's not what we're seeing?
Yeah, you're seeing like the after image of it, essentially. Like in the mainstream model, they say that the distances are so far away that the light coming to you takes time to travel. So what you're seeing is actually like where it was, a couple of minutes ago, depending on its distance and whatnot. So you're kind of seeing the after image.
So you're assuming that the star or planet behind the light is moving.
That is the implication, yes.
Okay. So you're using... All right, I'm going to say this really badly because it's mixed up in my head. So you're just going with where the star was at the time we can see the light for it.
Sure.
Kind of. So when we get to the occlusions and like the Celthio process, we're going to reference where the true position was, because the occlusion and an emergence is a physical process, which we'll get to here in a second. So we do end up referencing where the true position was. If you were to like conceptualize that as like this is the source of the light rather than the after image that we see, we do reference that. Like that's the primary separation from what we do versus how the mainstream globe would like us to conceptualize the positions.
Okay. I think I'm following what you're saying. Thank you.
Yeah, awesome. So like just real quick, if you think about, instead of a star being hella far away and whatnot, just think of like a flashlight overhead that's moving really fast and it's super far away. It's like, there's going to be like a little separation between the actual position of the light that you're seeing from the source versus where the source is at, if that kind of helps conceptualize it a little better.
Yeah. Yeah, I do think I'm following that now. Thank you.
Awesome. Okay, and then next up we have units of measurement. Now this is a really important concept because we often get told that units of measurement are mutually exclusive to a globe, all distances are globe distances, et cetera, et cetera. But what a unit of measurement is in terms of meters, I like meters. All the imperial units can be converted back to meters through multiplying it by like 3.993 or something, whatever it is. So they're all a ratio of the meter. So we're just going to stick with the history of the meter because everything has to be backwards compatible with that. But what they started with was using the terrestrial meridian for the length of a meter. And the terrestrial meridian is defined as the distance from the North Pole to the equator. So like a line of longitude going from the North Pole to the equator. And if you were to break that line down to 1/10 billionth of a segment, that 1/10 billionth would be what a meter is. That would be the distance of a meter.
So that means it's 1,000,000 kilometers from the equator to the North Pole.
Nope. 1/10 billionth is a really small number. The equator to the North Pole multiplied out in nautical miles or meters comes out to 6210 or 6218, depending on what you do. So if you take that 6218 number for kilometers, like that's what it would be in kilometers. If you break that down into meters, it would be like 6 million something, 6 million, 6218.
So it's not a 1-to-1. The meter's not like a 1-to-1 with the equator. I'm confused at what you.
10 million meters if you do it in meters. It's like these 10 miles. So you're getting all units mixed up, I think.
Oh yeah, sorry. No, it is
10 million or
1-to-1.
10 billion? I'm confused.
Oh, 10 million.
No, I said it wrong. It's 10 million. I was thinking of angstroms because what they ended up doing is redefining, well, by combining wavelengths of light. There's a unit of wavelengths called an angstrom. That's 1/10 billionth of the same thing. But so I got that confused.
So
yeah,
6210.
It's 1/10 billionth.
6210 statute miles, 10,000 kilometers, or 10 million meters. Those are all equivalent in this ratio system, right?
Ooh, thank
That's
you.
what I got. What Shane said, that's what I got from it. So I guess I'm correct in my understanding. So yes, I understand.
Awesome. Correct. Or awesome. And then Coco. So I know I kind of fumbled that a little bit, but if you think of like a string going from the North Pole to the equator, and then if we just cut off like a little bit of that string, that would be and then we use all units of measurement as a ratio of that little segment that we cut off, but it's tied to the bigger segment. You know what I mean? So it's all a ratio of the same thing. Does that kind of make sense?
Yes.
Awesome. And then that actual length is defined by positions of the stars where they're at and how we see them. So multiplying out a unit of measurement derived from the system itself is always going to be internally consistent. So what do I mean by that? Well, if you take 2 points of longitude, you can do the cosine between them, and you can get a distance. It'll calculate. They'll call it an arc circle, or what is it? The arc length. All of that is can be derived from doing the cosines of the latitudes. So so it'll produce a number in meters that you can traverse in meters, and it's going to be internally consistent. So in other words, you're not going to find a contradiction in pulling up like Google Maps and going like, okay, I live here. I'm 15 miles from the library. And then you get in your car and you go 15 miles and you're like, oh, like, it's not going to give a different number. Does that make sense? It's going to be internally consistent because that's how the whole system works.
Okay.
Awesome. And then I just had some more history on the meter and stuff here, but it's basically everything I just said. And then just the history of it. So if anyone wants to check out those, there's links provided there. And then here's the coefficients that link, or how you can multiply an inch back to the speed of light, because they got together in, I believe, the 80s and redefined it from a terrestrial meridian to the speed of light that it travels in 1 second in a vacuum. But you could link that to 239.37 inches, which comes out to be consistent with the meter anyway. So it's always, while it appears to be like a new separate unit of measurement, it's actually still just ratioed against the original terrestrial meridian for internal consistencies. Because if it actually came out to be like a different thing, they would have to like redefine distances and stuff. And we've never heard them do that, right? But sometime in the 80s they changed the the definition to the speed of light, and none of our distances changed. Well, the only way that would be possible is if it's part of the same ratio. And then what you can do further is you can actually break light into a spectrum and measure the physical wavelengths specifically and the distance between them. And so that's what they do now to define a meter, because it's super accurate. No worries, Coco. Yeah, the way they used to do it before was they had like a little, what was it, iridium bar or whatever, and then they would measure it at 0 Celsius or something. So it's like the wavelength of light thing is way easier to do. All right, so that was distances and then
So
distance
is that
calculator.
match the meridian? Like it's matching the meridian, but they just standardized it as like this wavelength of light, kind of like the atomic clock is supposed to match the solar
Yes,
year.
that's exactly.
But okay.
Yep.
Well,
Yep.
they took the same length and they were like, "Oh, this is no longer 1/10 millionth of a terrestrial meridian. It's actually 1/299,763 over the speed of light." And you're like, "Oh, ooh, neat." But both of them still equal 39.37 English inches. So the unit hasn't changed. What they did was historically recontextualize what they ratioed it against, but it still remains 1/10 millionth of the terrestrial meridian.
Oh yeah, okay, understood. Got it.
Well said. Well said. All right, then we got distance calculation, which I didn't put a thing here for, but we're all familiar with the Haversine, the elusive Haversine. It's supposed to be mutually exclusive to a globe because it requires the radius value to calculate with. Well, if we're dealing with a spherical coordinate system, which is latitude and longitude, and you're computing distances between it using central angle theorem and the cosine of that, well, you're going to need a radius for it to be, to use that. So that's all it. Like our position is that it's just math to calculate the positions between the stars. The curvature is in the sky, not the ground. But that's how we're not going to not use the Haversine. There's also a couple other ways we can do it, but none of the ways to derive distances is mutually exclusive to a globe. Although it is framed that way through the coordinate system being spherical. A lot of people say that the coordinate system represents the ground, etc. But this is going to be a test of that. But in terms of deriving distances, no matter where the curve is at, sky or the ground, this coordinates using the Haversine formula with the latitude and longitude and all that will yield the correct result because it is internally consistent. It's gonna output a unit of measurement that's a ratio of the original terrestrial meridian and or speed of light, which is just the same thing that Shane just went over.
Keep in mind, you can't have a terrestrial meridian outside of a latitude-longitude grid system because you can't get 62 statute miles unless you can do 90 degrees of separation. To get 9 degrees of latitude. You can do 69 miles per degree to get 90 degrees of latitude to get 6210. Only within that coordinate system is those calculations even possible. So then the unit becomes a metric of the coordinate system itself, which is what we mean when we say internally consistent.
Yes, sir. Well said. All right, now we're gonna. Oh, cool, dude! Canva's hilarious. It's gonna play both videos at the same time. 1 second. Gotta fix that.
Ooh, maybe you didn't pay them enough.
Okay, we're gonna watch a couple of videos real quick, and then we'll go over them. All right, a quick lesson on the principles of the cell Theo. So what we're looking at here is you can see the pattern of that light is distinctly different from the lights that are in this hallway here that are being reflected out into the mirrors or windows there. But what you'll notice here is that the reflected beams, so like this right here, gets reflected out into the images, and as we move over, we can see that when we intersect the reflected image, it doesn't block the light. The direct light source is right there, doesn't get affected when we move into the reflected images, right? The only thing that actually blocks that light is the physical.
Is his audio dropped down for everyone else or anyone else?
Overcome that.
Do you have stream
see
volume
the
up?
light again. Okay, so what we're looking at here as we move.
Gotcha.
You see now it's in the reflected image, no occlusion. Same concept as the cell Theo.
That's a cool video.
Thank you. Yeah, so basically, if we consider that street light the source of the star, and then, us moving back and forth to create the relative motion of what would be an occlusion of an apparent object, we see that the true source is unaffected by the apparent object. So it requires the intersection of the source and a physical object in order to cause an occlusion, and then also to see the emergence, we had to, move past it to to be able to see it again. And then we could take another look at that from a video from Taylor, where she used a laser pointer and a knife and a glass of water to kind of show the same exact thing. So we'll watch that now. No. Hi, this is me, Taylor. I have a laser and I'm shooting it into a glass of water. As you can see here, when it intersects with the physical object, the light gets occluded. When it's next to the apparent object, the refracted light doesn't get occluded, and you can see it sticking out through the refracted image. Thanks, Tay-Tay.
You could have asked her. She could have just done a live rendition.
Did you not just hear her? All right, so next up we have Goose, who made a little jig here to kind of show the same thing with the intersection point of the true object versus the apparent, and how it requires a physical intersection before it gets occluded. So here we have the jig with no refractive obstacles in between the light source and the object here. And we have this black one here. This is going to be our observer. So what we're going to look at is a camera on the ground here looking at this black object, and when it's lined up with this object in the middle here, we're going to see how much further this light source that's on the end of this has to be behind this before it gets occluded for the observer on this side of it. So to kind of show what that looks like, if you were to take a stick and line up these two, you would see that the observer and the object are, directly in line with one another. And when when there's no refractive medium between them, now obviously there's refraction in air and all that, but the distance is real short, so we're just truncating it to a nice clean zero here. But as you can see here, the angle of separation that's created to actually occlude the light source from the observer over here, when these are directly lined up, it's a really tiny angle here. You almost can't tell the difference here, but let me see if I can zoom in. See this little line here? There's definitely an angle there somewhere. So we can see that's a really tiny angle. But then when you put a refractive medium in between there, it's going to take that light source and bend it around it a little further. So it has to move further away to actually be intersected with the physical object in here, and not the refracted image of what's in here that the observer is seeing over here. So when you do that and you put the stick back, you'll notice that the angle is definitely bigger here, way bigger. So that's the significance of the occlusion being a physical process versus an apparent process. Now, a lot of what we started with when we were going through this self-theo and the process and everything, a lot of the globe lads wanted to add terrestrial and celestial refraction together as if a refracted mountain could occlude a star, and that's not the case at all. It would like set into the mountain, and then it would get occluded in the mountain. It would vanish while it's like inside of the mountain, if that were the case. So, let's see. I think
Hey, Alan, could you explain that just a tiny bit more? I'm just a little lost on that just a little bit.
Yeah,
I
got some. Go ahead.
I was thinking to maybe not bring up the mountain part when you were dealing with that, because I was trying to catch on, and then you started talking about mountains.
Okay, no worries.
And I got lost.
No worries. Let's say that this knife here represents the mountain. It's just a mountain, right? Like the physical mountain, as if there's no refraction. And then when you put this knife in this medium, we see that there's an extended version of the knife that comes out here. This is the refracted part of the knife, right? Does that make sense?
Yeah.
Okay. So if there's going to be an occlusion, the light source that Taylor's holding here has to be blocked by the physical light source. It can't be blocked by the apparent refracted, lifted up, reflected image. See how it's like sticking? See how the light source is like, it appears as if it's shining through the knife?
You should play it. Yeah, nice.
So it doesn't actually get blocked until it's physically blocked by the actual knife.
That's a significance.
Yes, sir.
Exactly, yeah.
Yes, sir. Exactly. So if the stars, if it worked the way that the globe lads were saying or whatever, we would see the stars going into the mountain before they get they would disappear in the mountain rather than being occluded right up towards the tippy top of it. So that is the significance there. The occlusions are a physical process. It can't be a refracted light versus a refracted image. They'll never occlude one another. So that's the significance of that. And then I'll play out Goose's jig video here. We can watch that. So this is from that perspective of being next, on the ground at that black peg, and then it's lined up directly with the object that's going to do the occluding, the yellow peg here. We got the lights, light source on the right, and it's going to move to the left, and we're going to see the occlusion differences based off of when there's no medium versus a medium. Same situation with the knife.
Wait, what's this part where we're seeing the peg separate?
This is when he's added a refracted medium in it, and we're looking at like a refracted image of it.
Is there supposed to be sound?
No, there's no sound.
Okay.
Yeah, he put that cup over it, this right here, that has the water in it. So now we're looking. So now
and he was just lining it up, right?
Yeah.
Super refracted though.
Yes, but yeah, that's what we're looking at as he gets that lined up. We see it's finally occluded there, and then he'll get the stick out and put it back, and we'll see that there's a change in the angle there. That's lame. At the end, we didn't see the end result, but that's what produced the larger angle there in that screenshot from the video. Sorry about that.
Yeah, I was gonna say that video maybe should have some kind of narration to
well,
to,
I did
explain
all
what's going on when.
That is fair. I did all the narrating before we watched it, but yeah, absolutely right.
Yeah, and I'm just saying that then when I went and watched it, I guess I was paying so much attention to it, trying to understand it, that I did not match up what you said with what was going on.
No worries.
Because-
we can do a quick recap just off of the screenshots if that's easier.
Well, I mean, I don't want to make you go back and do all that, but there was that. I guess there was just really two parts that it really started losing me, and the one had to do with when you said the new angle.
Ah, okay.
And
so
I didn't
let me
see the new angle.
Yes.
Don't show this. Don't show this. I do photography, so I know what's going on here. So this part confused me with what was trying to be said with the other part. But but the actual where you went and showed the angles with the pegs again, and right as he puts the refractive material back on it.
So basically, all he was doing here is just showing how much further the light source had to move so that it was still in alignment with the actual object.
And yeah, this part I got.
Okay, that's all. That's all it was.
Just another example showing it has to be physically in front of it. It can't be obstructed by a refraction. Although I do like the knife one better.
Yeah, so it's like if you were to take the knife
example, passes through.
If you were to say like how much further did Taylor have to move this laser behind this object if the glass was empty versus filled with water is all this was. That's all this was. Just showing how much further it had to be moved. All right. So if the occlusion process is clear enough, we can move on to stars in the ground.
So it's just that the image of a knife can't actually physically block light from passing through the medium is the whole point. Am I correct?
Yeah. Yeah, only the actual physical knife part could block it.
I mean, that makes sense to me, yeah.
It's pretty straightforward. Sometimes we tend to overthink it because it's like, like what are you saying again? But yeah, it's pretty much all it is.
So would you say that's why sometimes you could see like stars through the moon per se? Is it being refracted into a position to where you can see through it?
That would be a possibility, but I have never seen any stars going like I've never seen that. But I mean that would be the implication.
Interesting.
Yeah. All right. So we got stars. So we covered how the object in the sky move at a certain rate. That we could turn that rate of degrees into minutes and seconds of an angle, and we can also turn that into real seconds and minutes of time. So if we were to take the example of just watching a star and then we no longer see it anymore, did it get occluded by the ground or is it just out of our vision? Like this is something that's been, long contested on in the globe Earth versus flat Earth paradigm here. But so far we've agreed to, the motion and the treatment of how occlusions work, being a physical process and whatnot. So when we no longer see the star, we have two possibilities: that it was occluded by the ground because of Earth curvature, and it's now being physically obstructed by that, or it's out of our limit of vision. Now, like Noah pointed out earlier, when the stars are following the 15 degree per hour, when they get down to about right here, that's where they start to linger. And we can see what that looks like on a graph here in a second from our good buddy Brian. Let me see if I can pull it up real quick to show that lingering copy. Now, let's see, copy link. There we go. Copy link. All right. So if you were to plot that out, the stars, would ideally be following the celestial sphere, so they should be right on this dotted line. But as they get further into the horizon, you see they kind of deviate from that 15 degree per hour that's created by the celestial sphere, following that ideal radius. But that's all we're looking at there. And someone's microphone is a little hot while they're typing.
Got it.
All right, cool. So now we need a way to test what's causing the occlusion. Is it the ground or is it some optical phenomenon? Well, Mike ingeniously came up with the idea that we could use known elevations of mountains because that creates a new variable that's not just observation of a thing disappearing at the horizon. That can't tell us anything unique about the situation. We could argue our positions until we're blue in the face, but until we introduce another variable for this analysis, we can't come to any meaningful conclusion. But now we have a mountain peak. I'll start with the globe first, since it's most familiar to everyone on here. Now we can test now when this star should be occluded by the mountain peak, because we know how fast it's moving, we know the rate, we know how fast it's going to traverse the ground distance between us and the mountain peak, and we know when it's going. We can use astronomers' tools to look up references for where the true position of the light source is going to be versus the apparent and all that stuff. So now what we can do is we can, instead of using the horizon, we can now use the elevated horizon which is created by this peak here. So if we know the mountain peak, we just do some plain trig to get the elevation, and then we also get what the globe would predict for the elevation being lower. So on a flat Earth, the mountain is never going to be lower physically due to curvature. It's going to be the actual height. So we can compare the angles of the actual height versus the angle if there was curvature, just by subtracting out what the drop over distance would be from the elevation of the peak on the angle. Because the thing with trig is once you have two of the variables, you can derive the other one, and from that ratio. Go ahead.
Does everyone agree though that would be different for globe than it is flat? The time at which that star goes in front of that mountain, due to the geometric difference and drop over distance between the two, would occur at a different time. Do both people agree with that?
I don't know enough to agree or disagree with that.
No worries.
Logically,
yeah. Instead of thinking of the mountain, just think of the knife. On the globe, the knife is going to be lower. On a flat Earth, it doesn't matter how low the knife looks; it's always going to be the same height. So two different angles are produced by the math to make the prediction. Because on a globe, it would be physically lower, right?
Yeah.
All right.
You get that, Coco? Right? There's two different
I
predictions.
didn't get that at all. I have no idea
Okay.
why a mountain would be lower on globe Earth
globe?
than flat Earth.
It's tilting away from you. Think about it. Right? You got a flat Earth, right? Same elevation, pretty much.
So this is a mountain.
So the mountain would be physically lower if it's tilting away from you, if you think about it, right?
Okay, so we are assuming that this is a mountain that's somewhat over the curvature.
Yep.
Or yeah, essentially, yeah. Where the
Okay, so we're starting out with it lower just based on the fact of how far away we are from the mountain.
You got it.
The key fact is we're observing it from a certain distance away. Right.
Got it. Oh, thank goodness, because I really had no clue what was going on there.
You're good. There's basically two different predictions, and then one observation to decide which one's it's closer to. But go ahead.
So yeah, if you go back to that other slide, Alan, now we can look at when you were comparing the two. Yeah, so now we understand why those two would be different. So we both agree that that star would go behind that mountain at a different time for a globe as it would for a flat Earth, right?
Yeah, that makes sense. If you're a distance off from the mountain, on a flat Earth, the mountain would be whatever X height away. But on a globe, it would be whatever height X away, subtract from the curve, like how much it's curved down, and then also subtract a little bit off the top of the mountain for the angle that it's tilting away. So yeah, it would be. I have to agree that the globe Earth would predict it's shorter, right? Unless there's some sort of, unless we account for refraction, which I'm sure that's what they say.
Hence the point of the knife and everything else.
This is my favorite illustration though, because Roohif put it out. right? The Glober that all the Globers look up to, and our good buddy Roohif put this out. So it's not really a misrepresentation of what the Globe argues, and it quite explicitly shows the difference between the two. You don't really have to know about the angles and the distance. You just have to know that one of those mountains is higher than the other, right? It keeps switching from one to the other, and the bottom would be the lower for the globe. The globe has to be a little bit lower than flat Earth based on how far away you are when you're looking at it, as we all just agreed.
Well said. And yeah, Noah, real quick, what you said earlier, you can actually convert the drop over distance to an angle by just doing the inverse trig function for it, and then you subtract that from the angle from the flat Earth angle, and that becomes the globe angle. That's all this is doing right here, essentially.
I'm looking at it. It's nice. So that minus 202 is.
So that's the difference between flat and globe over 50,700 kilometers. It's 202 meters. Any formula you want to use, engineering, 8 inches per mile, will come out to 202 meters. So the difference between those two angles when we're doing basic trig is that drop in distance, is that drop over distance, 202 meters. That's why the top one, the only difference is that is subtracted from it. That makes the angle resulting lower. And right, so it's a smaller triangle, it's a lower height.
Wouldn't it be even lower though? Because the mountain would be tilting away from you slightly on a globe.
It would be exactly the drop over distance converted to an angle and then subtracted out. So instead of being 231, it's 217. Because like what we found out is that you know how they're always like, oh, that's just an approximation. That's just an approximation. Well, there's this thing called central angle theory, and what we found is that the drop over distance is always proportional to it's always half of gamma. Half of gamma is, I'm pulling it up now so you could see it. All right. Okay. So this gamma here is the central angle. This angle, this is derived from having two points that subtend a sphere. So what you're doing, when you would trig out the distance for this to get the drop over distance, it's always half of it. Yes, we use central angle theorem for it.
Oh, nice. Okay, yeah.
Yeah, so when they say like it's just an approximation, could be more, it could be less, it actually can't. It's always half of gamma. So and then the full amount, it gives you the celestial drop, which is we're kind of getting into some deeper concepts here, but it's not just an approximation, it's actually what it mandatory has to be to follow this trigonometry here.
I just want to say, Coco, don't feel bad for like not knowing anything. This has been a really awesome presentation so far. So with the back and forth and stuff.
Yeah, I wanted to say, Coco, you're doing great. Don't feel bad. You're crushing it. Clarifying the things that we overlook are great.
Interrupt whenever you don't understand or you think we screwed up or whatever, or nothing's clear. Yeah, whatever.
I know what I know and I know what I don't know. So, and yes, this is actually helping me a lot more than those other presentations. I'm sorry.
Yeah, no, well, a lot of them, we've been through some of the stuff and we're so familiar with it, we often overlook, stuff or like we'll make a giant leap and people are like, how do you get there?
Yes, and you're not the only one. I know that this happens because of my father. He was like way above everybody, so he often spoke way above people, and I had a feeling that's what was going on.
Nice. Yeah, well, the purpose here is to always make it as accessible as possible. So, like Shane was saying, if you need any clarification, feel free to just say, hold on 1 second, need help. Okay, so that concludes, I think we got the basic principles covered. We got angles, time, distances, physical processes, and the differences between flat and globe for physical occlusions producing different angles. Absolutely crushing. So now we can get into what I like to call the spreading of the sheets, which just means we're going to open up Google Sheets.
Well, so I don't know what you have planned.
Pause for laughter.
If you want to go through like the flagship example of Pikes Peak, so that we know like what we're talking, and then we can, because I think we need that. If we need to go through all the from beginning to end, I think distance, drop over distance, we have all the components, right? So we can work it out and why the two angles would be different, maybe. Because the rest of it is just going to be a bunch more data up based on this. So this is like the template, the rubric for how you do it one time.
Yep. Okay, so let's see. Let me see if I can pull up the video real quick. Download Celthea stuff. Unlucky. I didn't download the Celthea videos. 1 second. I was gonna show Mike's video real quick.
I think I have it.
Before we get into the data. Yeah, do you have it real quick?
I think that's converted and downscaled. Let's see, which one is that? That's 4 minutes, though. I don't know which one's 39 Aquarium in this video, though.
I don't even think that's Pike's Peak, big dog.
I labeled it Pike's Peak.
I'm gonna go ahead and say you mislabeled it.
39 Aquarium. Okay, how about this one?
Hang on 1 second. We're gonna do We're gonna do Pike's Peak, but we're gonna do not the 39 Aquarii. We're gonna do the one with the moon in it because it's cool as hell. So give me 1 second. Okay.
That is actually 39 Aquarii just below the moon.
Oh, nice, dude. Even better. Thank you, Mike.
I forgot you were here to help us out. That would have so much easier. Thank you.
Okay, so Coco, you know how I had that picture in Canva of like the globe and the flat Earth with the mountain and the star?
Yes.
Okay, so now what we're looking at is Mike with his video recorder, and he's facing a mountain, and we're gonna look at a star as it hits the mountain. So this is when we talk about, occlusions and doing the celestial theodolite, etc. This is what is happening here. So that star is following its 15 degree or so-called 15 degree per hour. It's actually at a lower angle, so it's not going to be at the exact 15 degree, but it's following that relationship there that we talked about earlier for that linear velocity. And boom, see it hit once it goes behind the mountain, it's no longer visible. So at this point of the agree or disagree, I think we can conclude that the star is no longer refracted for us as we can no longer see it.
Okay. And refraction is because we are seeing the light from the star and not from where the star actually was at the time.
Well, refraction happens. No, hang on 1 second. You kind of.
Okay, I messed that up. Okay, forget it then. Forget it.
No, you're good. We can make sense of it. So what we're looking at here is the refracted, apparent position of the star, right?
Yes.
And then as it gets down here, it's occluded. So what we're saying is that the true position, that laser light source that Taylor was holding, we can think of that as the star, that is now physically lower than the mountain, or not physically. It's a bad way to word it, but it's now lower than the mountain. And what we can determine from that is that because of the source being lower than the mountain, the apparent light that we see can no longer overcome the mountain.
I had a question.
So prior it was sorry.
Oh, this is the part that loses me a little bit. So when the refracted light gets blocked, that doesn't really speak for the source of the light, does it?
That's what I was saying.
Yes, because only when the light source is actually blocked is when we'll stop seeing the apparent position.
Well,
because like when we go back to this,
So you're saying it was being refracted or up above the mountain previously until
everything we see is refracted. Yes.
Right, but what I'm saying is the refracted light reaching your eye is what's being blocked, not necessarily the point source of the light.
No, that's specifically what's being blocked, the actual point source. That would be the implication. Because what we're going to turn around and do is reference where the true position of that star was, that light source was at the time of occlusion. And if it's at the same angle as the peak on a globe or on a flat Earth, that's going to determine the physical elevation of the mountain that did the occluding. Because if it was just an apparent object always, then it would never get occluded, right?
Right. What I'm saying though is if the light is bending, that light being bent, the target source, the target of the light is what's not reaching your eye anymore. That doesn't necessarily speak to where the point source is coming from. Right? You can block the light. If the light is bending, you can block the light without being able to determine that the point source is directly behind that.
No, only when the light source is blocked.
If we had to apply like a coefficient for the amount of refraction, when you no longer see the star, what would you apply? What would you apply it to? Be zero. Right? So you can't apply to nothing. If you don't see it anymore, you can't have an amount of refraction that you're arguing for.
Yeah, I get what you guys are saying. I think I need to think about how I'm wording what I'm trying to say. I'll get back to
no
you.
worries. No worries. We can do a quick recap of this part real quick. We kind of show the difference. So, although we're looking at this pretty much head on and we're pretty close to it, there's not much difference between where this lamppost is versus where we see it reflected in the mirror, right? But when we intersect it with another reflected image, nothing happens. The apparent and the source we still see. Only when we intersect it with the actual only when we get to a physical thing is when we stop.
You're all robot-y.
Sorry, how am I now?
Pretty bad. Sorry.
The last 15 seconds or so roboting, yeah.
Bleep blork.
I think it's because you played the video and you recorded it in high quality or whatever.
I'm still trying to wrap my head around the implications of this. Oh shoot, sorry, I didn't realize I have a hot.
No, you're good, man. I mean, anything we can do to help. That's why we do this every week, man. But let me see. I should be done lagging now. Testing 1, 2. Testing.
That's so good.
Can you go back? Can you go back to the video where you were showing with the
Yeah. So only when we get a physical object do we stop. Are we unable to see the reflected light source?
Right. So I understand that the mountain or the physical object is what's needed to block the light. It can't be a refracted object. I understand that part. What I'm saying is if you were to technically leave that same light source in the same spot and add more curve or take away curve, you would get a different point at which that object would block that light. Right? The point source stays at the same point, but the bending is affecting where it's going to get blocked.
Yes. That's exactly what Goose's thing was showing with how the angle increases because the physical intersection angle had to change.
So that's where I get a little lost of, okay, we understand the bending is what affects where it's going to get blocked, not the actual location of the source of the light.
Nope, it's the location of the source that light when it finally intersects with that they can no longer bend. That is what determines the occlusion.
So in this circumstance, the light source is the moving object, correct?
Correct.
Okay.
You lose me there, but I don't want to hold you up. It's okay.
No, you're good, man. I'll try and think of some more ways to break it down. But yeah, basically what we do is when the star is no longer visible for us. So in that video that we watched earlier, right, when that's no longer visible for us, what we do is we hop into Stellarium, we enter the coordinates of this peak, and we look at where the true position of that star was at the time, because we're considering that the light source, the source of, when it was once measured, taken from a zenith measurement, and then adding 15 degrees per hour for that, we're considering that to be where the physical source would be located. And then that's what we're referencing. So if that angle happens to match the angle for the observer there, then that means that the star is parallel to the ground. And what you could actually do is draw another triangle from the peak to the star, and then have a flat baseline from the peak, going parallel to the ground. And this angle would be the same as the original angle, which implies that there's no drop over distance.
That clarifies it very well. That's perfect.
So the time is the determining factor, right? Whatever the time that the star went directly behind the mountain, we convert that to say, all right, does that equate to 231 or 217? 2 degrees 31 minutes, 2 degrees 17 seconds. And we go to Stellarium and we look at the time, because we know divided by 360, as we started with, we can reference an epoch, which is just a starting position or a point of zero. We add the correct time to that, and we get the so-called true position of that star. We're using that position and its correlation to time to determine a model, because that time becomes our mutually exclusive piece of evidence. And so that's where we have to agree on that time, and then we can see whose model predicted closest to that time. In so doing, we're accommodating the difference between flat and Earth with the stellar occlusion.
Well said. And yeah, so here's what it looks like to hop into Stellarium. We enter the coordinates. Here's observer chords, and then we should have mountain chords somewhere. One of these two. But anyway, that's what we do to determine, what the cause of the occlusion was, because just doing it from the observer location doesn't actually tell us the cause of the occlusion, right? Because as we just learned, or went over, it's a physical process. So trying to predict it off of the apparent actually doesn't tell you why it was occluded. So the cell Theo gets has been divided into two separate analysis. One for the method that we're using. Oh, hold on 1 second. I lagged out again.
Keep fine.
No, my you see this red thing right here? I lost my stream connection. Not sure what's going on with it. It's super annoying. Give me 1 second.
Mercury is retrograde.
Man, that's so annoying. I'm sorry. I apologize, guys. My internet's not cooperating. Okay, it seems to be back. Okay. Let's see here. Holy sheet. Can post that sheet again. Absolutely. You want some sheet? One sheet. All right. Where were we at? Converting angles into time. So we're verifying what angle that star was at that time at the peak. And if that angle is closer to 230 than it is 216 or 217, actually, it's a rounding thing right here. This should be 217. But depending on which one that is closer, that determines what the cause of the physical occlusion was. And if the Earth is a globe, then we should be measuring an angle here when we go to confirm. It should be closer to what the globe predicts right here for Pikes Peak for the drop over distance. And it doesn't. Or it ended up being occluded at 233. So it was slightly higher than what we predicted.
Now, would the Globers just argue that that was just due to refraction and that's why? Or is that...
Oh, they argue something entirely separate. They argue that going to the mountain peak is not allowed, can't do that, doesn't work, this method's stupid, doesn't mean anything, non-physical, They actually completely reject that analysis on the face of it. They have never once accepted that as a valid analysis. They confine it to looking at it from the observer location and only the apparent position.
For obvious
Okay.
reasons, right?
Implications, man.
The implications, exactly. You can sense them coming and you don't like it, so you get off the road. Sorry, Coco, what?
So to be very stupid, where is this 230 and this 216 coming from?
Oh, no, that's a perfectly valid question. So, like I talked about earlier, there's two different predictions that could be made for globe and flat Earth. And all you do is just do rise over run for the peak. So we know the distance and we know the elevation of the peak because we can look up what the elevation is, and we know how far away from it we are because we can, enter our coordinates and then use a distance calculator to the latitude, longitude of the peak and get the distance. So that gives us our rise over run. When you divide those together, you get a degree in radians, and we can convert that into degrees, and that's all this is. So it's just dividing the elevation of the peak over the distance to the peak, and that gives us an angle.
Of where the peak is supposed to be or where the star is supposed to be.
Where the peak was at the time it occluded the star, right? That's what we're shooting for. Right?
Yes, great question. But it is the peak, and there should be no physical relation to the occlusion and the peak at that elevation if the Earth is a globe. So that's the significance of it, because if they both match, then that means we can make a congruent triangle, meaning we could just say that this angle for flat Earth is the same as the angle from the peak to the star, because that's what it would imply geometrically. I think we have some images of that, what that looks like. Here we go. So ignore all the math on here for now. Just look at the triangle. We have a distance of 50 kilometers, and we have an elevation of the peak of 429 or 4,299 meters. We can divide those into each other and get an angle that's 231 for the peak, as if there's no drop over distance. And then when we take when we record the occlusion and the time, and we go to the peak in our favorite astronomer software, and we look at where that star was at that time at the peak for its true position. If it's also 231 or thereabouts, well, now what we can do is, you see how this white arrow turns into a blue arrow that just keeps going, and then we have another white arrow that goes off the side here. That's making a congruent angle off of the first one, and that would only be possible if the Earth were flat. Otherwise, the angle that it would produce would be congruent with the globe angle here, which would be 217, but it was congruent with 231.
And again, the difference between those two is just 202 meters. That's what the difference between 231 and 217 for an observer who's 50.7 kilometers away, and respective on a flat Earth or a globe Earth. It's only different 202 meters. So the mountain would be 202 meters lower for a globe, which is why you get 217.
Do globers claim refraction from the star to the mountain?
They claim everything.
They do, and also they also claim the refraction, like terrestrial refraction. So they also they don't want to agree to the 217 angle. They want to add two arc minutes of terrestrial refraction to make it 219, because that's what a terrestrial theodolite would measure. But we're not interested in the optical for number one, and number two, the refraction wouldn't, as we just went over, the refracted mountain would contribute nothing to occluding the star physically. So that's not even a tenable position.
And number three, when you add it, it doesn't even make it closer. We still are much closer. So it fails 3 times.
And on top of that, I was looking through the differences between astronomical refraction and terrestrial, and I found some great resources from Andrew Young, who's like one of the most prominent and cited globe lads that covers refraction. He actually goes over the history of how they tried to merge terrestrial and celestial refraction back in the day for geodetic surveying and whatnot, and it leads to a ton of problems. They can't do it, and mechanistically, terrestrial refraction is governed by like this really low boundary layer that's basically created from a homogeneous gradient due to heat from the sun and radiating from the earth and all that. So like there's this really small band of terrestrial refraction that light is traveling through to even be applicable for. The light coming from the stars does not interact with that boundary layer at all. So they have an entirely separate model for the astronomical refraction. They do explicitly do not mix together.
So, and it's probably a model that's never been tested. It's just theory, I'm guessing.
Oh, not only is it theory, it's a curve fit specifically so that observation.
Right.
Get the observation to make it work still on a globe. Get into these lower
like
angles
crazy
of
again.
refraction. Yeah.
I think you're back.
Yeah, hold on 1 second. I'm gonna end my stream, and then you just keep it going, and I'll just upload it later. And maybe this will.
I'm not. I wasn't streaming at all, so that's not gonna.
That's
That's not gonna work.
Well, I ended that prematurely. Would you mind? Would you mind just firing it up real quick so we can have a continuation of this?
Jesus,
It's
okay.
fine.
All right.
Geo has it. It's all on Geo's thing anyway. It's
Yeah.
fine.
Yeah.
All
Hey,
right,
so if you brought that distance out far enough to where the mountain peak was at the horizon, would it still be the same angles?
Ooh, great question. So we actually, doing this congruent triangle situation, since we have the occlusion, you can actually trig this out to the GP of the star. So you can do like, is Brian here? I forget the numbers that he did on this, but like, yeah, we can do millions of meters of distance to like on this congruent triangle. So the answer to your question is yes. And not only that, we can show it.
Okay. So it is replicable.
Mm-hmm. Let me see if I can find Goose's simulator real quick.
I have a simulator. I don't know which version. There's one.
There you go. There you go. I linked it to you so you can have a copy. So here we have the celestial sphere on a globe, the way that they conceptualize it by doing the geocentric transformation. And then we have flat Earth with a celestial sphere for the observer. And this is plotting out the eclipses or whatever. But what you can also do with the mountain or with the occlusions is when you, instead of just using the distance, shoot, where's that? Nope, where's that one at? Hang on 1 second. I closed it. One second. Sorry about that. Need to reopen copy. Okay. So instead of using this 50 kilometers, what you can do is after you get to the peak, you can do the distance to the GP of the star, which can be, it's usually a couple thousand meters or kilometers, and which comes out to be, millions of meters or whatever. But it's the same exact relationship. So this just gets bigger. So the distance goes out to millions of meters, and then the baseline here goes up to the radius of Earth essentially. So it's like 6,731 kilometers. So it's like we end up with the exact physical interpretation of. 1 second. Celestial theody, old celestial. Yeah, this right here. Copy link. There we go. So essentially, we end up creating this where the elevation is 6,371 kilometers for the altitude. Now, they always want us to conceptualize the altitude of a star as an angle rather than a physical number in kilometers and stuff, because that would start to show some equivalences that aren't liked. But this is exactly what we can do with the celestial theodolite. So we can turn this, we can make a little triangle here from observer to a peak, and then that angle will correspond to the position of the star at its GP over this distance, and it'll be at an altitude of 6,371 kilometers.
Every time that 6,371.
Pretty much, that's exactly what is mapped out in. Oops, 1 second.
Well, so
Finding
that's
more
the radius, 60-30 kilometers, like 39-59 miles.
Pretty much, we can turn this, we can make a little triangle here from observer to a peak, and then that angle will correspond to the position of the star at its GP over this distance, and it'll be at an altitude of 6,371 kilometers.
Every time that 6,371.
Pretty much, and it'll be at an altitude of 6,371 kilometers.
Every time that 6,371.
Pretty much, that's exactly what is mapped out in. Oops, 1 second.
Well, so that's the radius, 60-30 kilometers, like 39-59 miles.
Yep.
Right.
Oh, that's Earth radius. Or that's celestial sphere radius. Sorry. I'm not up to snuff on my numbers.
No, you're good. So check this out. The terrestrial sphere, Earth, they say, has that radius of 6,371 kilometers. And a celestial sphere is actually a sphere of infinite radius. But if you want to use the celestial sphere on the Earth, you have to merge the two spheres. So they do this via what's called a geocentric transformation. So they take the perspective of moving, instead of being on the ground here at the surface of Earth, they do a transformation to the center, and the celestial bodies move over top like it's in a hollow shell.
Around everyone. They model it around every, it's an observer centric, right? So everyone can use the same method because the stars rotate around everyone. So only if that were the case could you just migrate the thing to the center and then use the same angle measurements for everyone.
So that's pretty damning in itself, then.
It's not great for them. It's not great based off of the occlusions and stuff, because if it was just based off of the math without the occlusions, like we're just arguing math equivalences and what could be, but with the occlusions, we now have another, an independent variable that's been changed that can help us determine what's going to what's going on with the stars. Are they following the geometry of going around a ball as we're rotating, or the sky would be moving over top of us? Either one would be equivalent. But what we actually show is that the stars are like the true positions are not actually going below any sort of ball. They're always parallel to the ground. That's the only reason that we could do that congruent triangle thing, where we can go all the way out to the GP of the star. So that it becomes extremely damning when combined with the occlusions. And then we also did the same thing. By we, I'm taking credit for Brian's work, but Brian plotted out the eclipses using the shadow length as the distance, and then taking deriving the elevation of the moon at every for an observer along every point of latitude for that shadow. So then using that, he did another triangle, basically use the moon as the mountain for the occlusion for the eclipse. And then when you model that out, you get this. Now this is what the data plots out. So as the change over distance occurs for this eclipse, as the totality changes, the sun and moon never glow below the horizon. There should be, like, I think it was 4 million meters of curvature of change. Now on the globe here, what they predict with their model being, predicated on the ground being physically curved and the bodies being off, whether or not we're rotating or the sky is moving around us. If it's a globe, the true position also has to change in elevation, and that's not what was shown. So this is what it should look like. If globe, this is what it did look like. See how these are parallel to the ground?
Yeah.
So if
It's actually a good.
There should be another celestial sphere here. Yes. So.
Oh, he did them both.
When you
I was going to say.
yeah. When you zoom out here, this radius of 39 and 59 extended out to a celestial sphere observer on a flat Earth is what we're looking at, versus what it looked like, what it was supposed to look like on a globe.
But I think that's
So
a
on the
good
flat Earth,
visualization.
that 3959 on the flat Earth would be your limit of vision, basically.
That's our position.
But no, the quote unquote celestial sphere.
Same thing. That's how you perceive the heavens in that radius of vision. They just mapped it out accordingly.
Yeah, they just filled out the bottom with math to give it negative coordinates and a spherical coordinate system. Everyone observes the same hemisphere all over Earth, right? Everyone sees half a sky. You can math out that half of the sky using spherical trig, it turns out, except you just fill out the bottom with abstract fantasy math, and when you describe something that's already set. And of course, it's based on the circumference value, so that by the time it circles around the Earth, you can do some math that says actually it goes beneath your feet in a circumference of equal length, and you can have the same predictive power for when it will come back around, and you'll see it the next day. Works for everything in the sky.
Gotcha.
What about the Antarctic sun, Alan? What do you think's going on there?
Well, with the internet being spotty and whatnot, and this being a really good session of covering the fundamentals and whatnot, I think we did a really good job of having a clarifications for everything, man. That was awesome. Thank you, Coco, so much for participating, and thank you, Noah. Shout out to you, lads and ladettes. But
Thank you, Alan.
Definitely clear.
Thank you for going over it, because it was really getting hard to follow every Monday. So thank you so very much.
Yeah, no worries, man. It's always good to go back and cover the basics and stuff. But yeah, when we pick up next week, we will go over. So now that we've covered some of the basics here, we'll do a quicker recap next week on that, and then we'll get into analyzing.
Lost you there again.
Oh, my mic or what? Did I lag out?
No, yeah.
Just lagging.
Yeah, like that.
Son of a gun. All right.
You guys
Yeah,
every
so
Monday night now. I've been out of the conversation for quite some time.
Every Monday we come back now.
Okay.
Yeah, every Monday we will be back. We will recover, and then hopefully we'll get some new data with the bounty that we got out. So tell your friends that there's a bounty for celestial theodolite measurements, and all we need is their observer location and latitude longitude coordinates and the time in which they started their recording.
Awesome.
And
Good
that'll
job,
be good,
guys.
because the two things that still are just not making sense to me. Number one, that knife in the cup. I have no idea what that's supposed to show. I mean, I know it's refraction, but it's a different kind of refraction to me, and it never comes to a conclusion in my mind. But I'm still having, and I'm not going to make you re-explain it, because I think I'm getting to a better position where now I can pay attention better and try to pick it up. But some more basic concentration on the whole process of the occlusion behind the mountain and the different measurements, I think would be very helpful.
Yeah, I meant to go through all of Pikes Peak in one example, but I think we had a lot of time. Went through a
So
lot
from
of the
what I
basics.
understood, the time is the biggest variable, correct?
The time determines the angle. Yeah.
Mm-hmm.
Yeah.
An angle is the mutually
So it's
exclusive piece of evidence.
I think
so. It's when that inclusion takes place, or
if I'm correct, then the knife example just shows that the refracted image of the knife, while the refracted image is overlapping the light source, it doesn't block it. But you only get an obstruction of the light where you can't see it anymore from the observer's position when they're all in line physically. Is that correct?
Nailed it. Sorry if I was lagging. Yes,
Which the
that's
only
correct.
difference variable would be the time on the globe or the flat Earth, correct?
Well, the time corresponds to angle, and the difference between
Corresponds to
flat
angle,
and
yeah.
globe, the globe would have a lower, smaller angle just because of Earth curve, Earth drop. And that's what we're trying to do is try to test, is the Earth physically curving at that rate? And we're using an outside or external reference to do it, right? We've all been doing this for years. You talk about surface level observations back and forth. No one will prove anything to anyone. It's all internally consistent with refraction and the coefficients being tied to the Earth's radius, etc. Arcing that, and even an arc of light is said to curve over at the radius of Earth. So how would you ever know if it was flat or curved to begin with? So that's why we spent so much time on this example for an outside comparison, so we can test it externally using the stars. And it turns out every time we do that, it looks pretty flat.
Yeah, because they built the globe off of the observation, correct?
Indubitably, and then they transformed it to, using and made it in binding angles to time. They've presented it such that it only works because the Earth's a globe, and you have to use this coordinate system to traverse it based off of time. But it's just literally merging two star maps together, one from the north, one from the south, binding it at that central, at the center of that radius for the observer, and that's all it is. Big Dog, please explain apparent position to me as you understand it. That is the position of the star that we see.
That dude sounds like a troll. I don't know.
I don't know. I mean,
Alan, I just tagged you in the question I was trying to convey earlier. I don't know if that's a good illustration to make sense of it, but I added the green stars as part of my point.
yeah. So which one of those would be like the actual position? That would be true position?
So yeah, if we the two green stars are hypothetical actual positions, just to make my point.
What is your point?
That basically the path of the light being blocked, that being occluded, does not determine where the actual point source is.
It's completely dependent on it.
I think what we would need to see is an example similar to the laser in the cup or the pin on the thing, showing that it doesn't matter and that it actually changes upon the refracted image, and then we can discuss it. I think I see what you're arguing, right?
Okay. Yeah. No, that's a good point. Okay. I'd have to put some time aside and try to actually set up a video or something, but yeah, basically just my point is that I get everything you guys are arguing besides the fundamental principle that the light being blocked determines where it actually is. I don't agree with that part. Everything else I think I'm on board with.
Cool.
I think maybe that has to do with the fact that I don't think we actually got to cover that because we got diverted into different things. So maybe that's going to be partially what's going to be covered next week.
Yeah, you want to do that next week? Are you down again?
Absolutely.
Yeah.
Nice. I want to go through an actual Pikes Peak example with the distance, the elevation, the difference between the two, just so we can iron home the process. But I think we ran out of time.
Yeah, that would be really, really nice. Because like I said, that was where I really stopped getting it. But again, if anybody throughout the week wants to reach out to me to go over this whole cup thing, I am telling you, this cup thing, I get that the cup thing is refraction. I don't get how it has anything to do with the occlusion behind the mountain whatsoever. I don't get it. It doesn't make any sense to me.
Well, I will give it some time and think of some more analogous ways to represent it.
I can give it a whack real quick. So Coco, the knife is the mountain peak, and what that laser light is showing is that you can still see the laser light when it appears to be going through the knife, but because of the refraction, right? But as soon as you go to a certain point, it doesn't matter how much is being refracted, it disappears because it's actually being occluded by the knife. So if you take
Which
that to the
is
mountain peak, right? If you
Okay,
take that to
but
the
in
mountain
the
peak,
which is the lingering of it there. You know, like you said, the lingering on the horizon or above the peak.
yes.
but it's not the same type of refraction, and I spent too much time trying to make it fit with the other examples, which made me lose other stuff, because that's a refraction that's not only going through the medium of the water, but it's working with the side of the glass, and it's curving around the knife. And when we watch the occlusion of the star, there was no curving around of anything, or
That's a feature, not a bug, Coco.
Yeah,
what do you
that's
mean?
Go ahead.
I was just going to say that's a result of you not seeing the medium between us and the star, like in the example, but that's just the angle the star is hitting our eyes.
Yes, and what that further implies is that even though, it might look lower and compressed and refracted, the physical elevation of it still includes the star when it intersects with it. That's the important part of that. That's an extremely important concept of it. That's why it doesn't linger or go through the mountain like that, because it's already past the threshold where it would physically get blocked. And then we're interested in what time that was, because time equals angle.
Yeah.
Yeah, and all that I'm starting to get with the mountain. I surely cannot be the only one that is not getting this.
Just imagine if the mountain was like a refracted image, just like the knife, then you would actually see the light like behind through the mountain, just like you
Bingo.
saw the light through the knife. If the mountain itself was a refracted image, you would see the light through the knife. So through the mountain, sorry.
Well said.
So is it like an opposite example?
No, it's showing that the physical outcome in reality is that when it intersects with the mountain, it gets occluded, and it's not being, refracted over the thing and all this stuff as it's asserted. Because like when there's nothing to do the occlusion, the difference between the true position and the apparent position is just made up by however much refraction there needs to be to explain it. So that's the amount that they say of like a physical medium in between the starlight and us is changing that path of light. And then what we're finding based off the occlusions is that amount that they attribute is not even close to it, because like you just noted, mechanistically it's pretty much canceling out as soon as it intersects with the peak, instead of lingering into it, or even like going into the refracted part of it a little bit and then being occluded. It's doing it pretty much right at the top of it. So
Right, which is not what the laser in the cup does.
Right. What the laser in the cup does is should be what you would see on a globe, counting for the amount of refraction that they say is existing to lift it up over the mountain. But what we see in reality is the almost instant occlusion.
Oh, wait. So you're saying the laser in the cup is supposed to be what globers see?
No, it's an analogy. The knife is the mountain, the laser is the starlight.
And
It's
you're saying that
it's an
example is what should be seen on a globe Earth.
Yeah, I think so. Yeah.
Or not even just on a globe Earth, but just in general, if the occlusion is non-physical, just if there's any refraction or anything going on at all between, like if that mountain isn't the physical mountain, then you would see the light going through the mountain like you do the knife in the glass. Same situation.
Because they explain away being able to see that mountain at some distance due to refraction, correct?
Okay, so I'm not going to keep taking up
Okay.
your time over this. My brain is just saying I don't understand this. It makes no sense to me. Again, if somebody wants to reach out to me about it at a later point, that's fine. I just don't. It makes no sense to me. I'm so sorry. It just doesn't.
Really different. And by the way, if I'm wrong about this, like the people more schooled in this could come correct me, right? Imagine that mountain, just like a hypothetical situation, right? Imagine that occlusion behind the mountain was happening to a mountain which should be blocked by the curve. Imagine, right? So it's a completely different situation. So imagine that mountain was supposed to be completely blocked by the curve. I know it's not in this situation, but I'm creating a hypothetical. So imagine that mountain was supposed to be completely blocked by the curve, and we see the mountain, and then the Gobers said, "Hey, look, that's just a refracted image of the mountain." Then we'll be like, "Oh, cool. So if it's a refracted image, when the star goes behind it, we should see the star through it because it's just a refracted image." And we know through the local test or observation that these guys have done illustrations, that when you have a refracted image of something, you can see light through it.
Mm-hmm.
And then the light goes behind it and, oh shit, it's instantly blocked. Well, then that can't be a refracted image because light comes through refracted images, but light gets blocked by actual physical objects.
Well said.
Bingo.
Absolutely crushed it. On point.
That was great. There we go. There we got it.
All right. Well, Coco, again, thank you for your time. We will definitely come back to it next week. And was that Babby H. Boone, PhD? Well said. Thank you for the assist, my man. And Noah, thank you for helping out there as well. And we will come back next week, lads.
Okay, thank you, Alan.
Thank you. That was great. Amazing.
All right, we'll stop the not stream. Oh wait, no, I was recording.
Oh yeah, we'll start the non-stream. Okay. So let's see. Tomorrow, Tuesday, we'll be doing a reading night. We'll be going over a superluminal paper that Piezo found recently. Looks really interesting. And then Wednesday, I'll be going over the Cell Theo again with Jaren from Jarenism, the flat earther formerly known as Jaren.
A flat earther formerly known as Jaren. I like that title.
That's awesome. And then Saturday, Shane and I will be going into a debate against some Czech lads who seem to have a problem with the null hypothesis or something in regards to the celestial theodolite. So we'll see what those lads have to say about it all. That'll be at Saturday at 2 p.m. And then we'll be back again on Globebusters for Sunday. And then we'll be back here on Monday for Celestial Theody number 25.
So where are you going to be tomorrow?
We'll be streaming in the Ether Cause Discord, doing a reading night. And then that'll also be on YouTube. So here's our link to our Discord. And if anyone would like to participate in reading night, we do accept people to join. Like, if anyone wants to read out loud in front of other people on the internet, that would be awesome. We do appreciate when someone comes in to read. But that'll be tomorrow at 8 p.m. Eastern.
So how you guys met Piezo? Did you just come in and ace a reading night and you were like,
Dude,
what, bro?
No, you know how I met Piezo, bro? He was on Earth Awakenings and he was going over Battle of the Beams. And I remember seeing Battle of the Beams, years ago on
brought up that. I
Globebusters.
forget.
But he, you know how Piezo does that thing where he whips out MS Paint and draws diagrams? Bro, he bodied everybody with Battle of the Beams on that. And I was like, I need to be friends with this guy.
Nice. I like that feeling. I like finding that in the people.
Yeah. Piezo just doing Piezo things. All right. Well, we'll see you guys later. Catch you on the next one. I'm going to head over back to the old ACDC.
Look how much easier it is without people actively distracting, kicking up mud, throwing ad homs, and just generally trying to disrupt with obfuscation and distractions. Noticeably different.
Yeah, thanks for all the clarification, guys. You guys rock.
Dude, that was really good, man. Fucking hell.
Did you say you want us to
Just
get paid NASA shilling here or something for you?
did request him specifically. Is he around? Can we page him?
Dude, those physical illustrations were just like perfect. That made everything fucking click. It literally didn't click for me until I saw that. Now I understand completely.
We actually have quite a few Desmos models now, which I think have really helpful in understanding the difference between the two. Our buddy Goose did a good job programming them to be automated. So you don't have to click or move or understand. You just open it up and watch. And it's like, oh, I can clearly see the difference. Now I understand what you're talking about. Or at least it helped me. But yeah, apparently the Czech lads have dissected this whole process and have destroyed the whole argument. So we're gonna go see what they have to say on Saturday. Should be devastating, I'm sure.
Devastation. Y'all have a good night. See ya.
You sound scared when you say that, Shane. Could you, maybe divulge some of your feelings on that real quick? Oh man, he's gone. He dipped just like that. You see how he obfuscated the question?
The guy who asked the question earlier and said big dog and they didn't know who it was. There's only one guy in this arena that uses big dog like that. It's Jazza, the crazy drunk helicopter pilot from Australia.
Yo, what up, big dog?
He's the only one that uses big dog like that, bro.
Who is?
Hello, anybody? Does the globe make good predictions?
Yeah, they're science fiction predictions, though. You know what I mean? This ain't like a scientific prediction.
Well, are you a
Makes great
globey, Jeremy?
predictions.
The predictions are honestly meaningless. Like if we have a clock on the wall and neither of us can touch the clock, see through the clock, look behind the clock, we can make all kinds of predictions on, based on either model. I think it's a cesium atom oscillating. I think it's a pendulum moving. I think it's two midgets turning gears. Whatever it is, you can make predictions on where the thing's going to be, but that doesn't mean it's your dwarves turning a gear or the cesium atom or the pendulum. It could be something else. You know what I'm saying?
Wait, are you a flat earther? I'm a flat earther. Wait, are you a flat earther?
Jeremy's not a flat earther, he's a glober.
Okay, so Jeremy, does the globe make good predictions?
The globe makes predictions, but like I just said, you can make the predictions with anything, though. It doesn't even matter.
Okay.
Did you hear
so
the clock
how
analogy?
far away?
Well,
So
let's not
yeah.
deceive.
So
Let's not hold on. Jake is trolling. Let's not deceive him though. Jeremy's not a globe guy, so let's not deceive this guy.
I was just gonna ask, how if the globe makes good predictions, how far away does it predict the horizon would be for a 1 foot observer?
1 foot? I don't know. A mile or something? Yeah, I'm not a globe. I'm a flat earther, dude. I'm on your side, so.
Oh, okay. See, I always set him up with that one.
I mean, they're not predicting it. Yeah, they're not predicting distances to the horizons very good. I hear you.
Dude, imagine if someone made a to-scale fucking version of the Earth. Like one would be like a globe, one would be like a flat Earth with a fucking firmament around it, and then do the celestial theodolite on that with a refracted
Like
light.
a 1-to-1?
Oh well, whatever, as close as you can make it. I know they have 93 million miles, some sort of ridiculous ratio, but like something that could be equivalent.
Wait, Arul, are you a globe earther? Who in here is a globe earther? Anyway?
Globe Earthers, bro. They're not yet. They'll come. They're on their way.
Oh yeah, no, I'm a diehard globe earther.
Oh yeah, but
Oh yeah. Wait, wait, Matthew. So, does gravity coalesce things into balls? The more mass it has.
Yeah, it can happen.
Okay, so what has more mass, the Earth or the Milky Way galaxy?
The Milky Way galaxy.
So why is the Milky Way galaxy a flat disk?
It's spinning too fast.
The Earth is spinning too, and it's a globe.
Right. It's not spinning fast enough for the amount of mass it is.
Oh, so now things with
The
mass that
universe
are
is
spinning
flat.
are flat disks.
No, it
So
depends
now
on it depends on how fast it's spinning and how much mass it has.
your argument was that things with more mass coalesce into balls, but the Milky Way galaxy, like we established, has more mass than the Earth and the Moon and all these other things, and it's not a sphere.
Right. It depends
Because
on
it's
both mass
spinning.
and how fast it's spinning. Right.
Yeah, and more importantly, the density of that. What's the density of that object versus how
Can you
fast
give me?
is it rotating?
Yeah, can you give me those parameters on when it starts to
No, I
coalesce
can't. I
into a
have no
ball?
idea.
Dude, I
So if
saw
you
on
have no idea,
TikTok
then
or YouTube. Sorry, go ahead.
I was just going to say, if he has no idea, why are you making a positive claim then?
Oh, I'm
Because
just
this
saying
stuff has
how it
already
is.
been modeled by the best and smartest minds in the world and supercomputers, and has been demonstrated to work perfectly
like
mathematically.
Also,
like
it's
the
not
three body
wrong because
problem.
I don't understand it.
Wait, like the three body problem, you mean? That's been done by a supercomputer and solved, huh?
But you have a problem with the three body problem?
It doesn't. It's not been solved. It's not been solved on a supercomputer. So
Yeah,
wait,
you
you're a
can't
flat
write
earther.
Okay,
equations.
so just
We
the
have to
fact.
do
Hold
it.
on a second. Hold on. Because there's a three body problem. What do you think that means? You think that means that?
You just said everything's been mathematically solved, and it hasn't.
There is no. There is. It's not that there. It's not that it hasn't been solved. There is no mathematical solution to the three body problem. In the form of a simple equation.
Right.
There's no.
So then, why did you say that mathematics has been solved for everything?
When we're talking about on those scales, this stuff has been mathematically solved. What do you mean? The
Like the
orbits
three
can be
body
explained.
problem that we just said.
The orbits
Like the
can
three
be
body
explained.
problem.
They can't be explained with one orbit. So what?
So wait, are you a globe earther, Jake?
No, I'm a flat earther.
So why are you defending the globe? I don't get it.
He's lying.
Bro, he's trolling. Obviously, he's a globe earther. Come on, man.
He's troll lying again. He's a globe.
But let me ask you this: do you think that just because the three body problem, because when it comes to the fact that there isn't one simple mathematical solution to it,
No, I don't think
you
there's any
think that in
evidence of a
some
sphere.
way that means that it's not mathematically solved?
Yeah. It's not mathematically solved, correct? Yeah.
That's just silly. That's just that because you don't have a problem with electric fields, right?
Wait, hang on a second. Before we wait, but we're both flat earthers. Why are you defending the three body problem?
I'm not a flat earther. I was kidding.
He's not a flat earther. God damn it, bro. Why can't the modern day?
Oh, okay. So hang on a second. Wait. So what's your number one? Like it's 2025, right? What would be your number one best?
Well, I want to
evidence
keep
to prove
talking
the globe?
about the three body problem. You have a problem with the three body
You mean
problem. So do you think that
you mean the one that
we
wasn't
don't have it?
solved?
Do you think that because of the three body problem, do you think that we don't have a good understanding of electric fields?
No, I think you said that the mathematical formulas were all they all worked with the globe. Yet we have a three body problem that mathematically can't be solved.
Yeah, we have mathematics. Well, hold on. You just because not everything in our reality can be explained by one simple equation. That doesn't mean that it's not mathematically solved. It just means there's not a simple
gravity.
mathematical solution. Mathematics is just a
Right.
model of our reality. That doesn't mean that everything within our reality can be modeled with a simple equation.
Like the weather, you don't have a
really?
precise equation to predict the weather. That doesn't mean we give up.
So
Yeah,
hang on a
it's
second.
just silly. And
what
you
evidence
wouldn't
do you
argue
have?
that for electric field theory, right? Electric field theory is what's created all the amazing technology we have now, and electric field theory is dominated by the three body problem as well.
Great. So
So I don't
what evidence do
understand.
you have that what evidence do you have that the Earth is a spinning globe in outer space?
Oh, okay, so you want to abandon the three body problem argument now?
Well,
Are we
yeah,
just
it's
going to
not
abandon
mathematically
that?
solved. Yeah, it's
Jake,
not
I don't think they
mathematically
can make
solved.
much progress anyway. So
Yeah, it doesn't sound like it. Yeah, so if you can't explain everything in our reality with one equation, it's not mathematically solved. Is that where you're going with?
Right. Right. Well, we both agree then, right?
No, it's just stupid. Honestly, it's
I
just
agree.
dumb.
I agree. So, what's your number one best evidence that the Earth is a globe in 2025?
the fact that we can accurately predict the path totality of an eclipse, and you can't do
Oh
that
my
on a
gosh.
flat Earth. And I know that
Oh my
I
gosh.
know you
That
guys
was
want to
some.
say that
That was
one
some.
guy who literally used the heliocentric ephemerates.
Oh, come
Okay,
on
so
now.
first of
Yeah.
all, it's not a solar eclipses are not a prediction; they're a post-diction. They're just something we observe in cycles and then attribute a date to it. It's not a prediction.
No, the path of totality is unique for every eclipse. There's no cycle that you can use to predict the path of totality.
There are
Every path of
absolutely
totality is.
there are,
You just missed that
the eclipses are on
presentation.
cycles. The eclipses are on
You know the
cycles.
Okay,
presentation.
so tell me this next eclipse in Egypt in 2027. What eclipse path of totality in the past perfectly mimics that one?
Okay, so hang on a second. So first of all, you're saying eclipses are your best evidence that the fact that
I
you can
said the
predict
path.
them.
I
Right?
didn't say eclipses. I said the path of totality, which not only
The
requires you to
path of
know that there's an
totality.
eclipse happening, but it requires you to know
Right.
some very important alignments within
Like what?
three-dimensional space. You have to know the alignment
Okay.
of the sun, the moon, and the earth within three dimensions, as
Right.
well as the layout of the topography on the earth and any shapes related to that, so that you could carve out a path for that shadow. And not only that, predict when that shadow will arrive, how wide it's going to be, and where it's going to be at any given point on the surface, down to the second. That
Okay.
shows you that you
So
have a very profound understanding of this
so you know
of
that
the three different objects.
there's a kinematic equivalence between heliocentrism and geocentrism, right?
Sure.
Okay.
You could
So then by
you
predicting,
could
hang on a second, I'll let you waffle. So then by saying that you can predict what's going to happen in the sky doesn't prove heliocentrism then.
that's a little bit different than what you're talking about a kinematic equivalence of setting up the coordinates earth centered versus sun centered. That doesn't matter. It still
Yeah, the
requires
kinematic.
a
So why are we
spherical
talking
Earth.
about it?
It still requires a spherical Earth. It still requires space to be
Oh,
real. It still requires the
hang on a
objects to
second.
be within space with a given size and a
So
given dimension.
it requires,
What coordinate system you base it out of is irrelevant.
so it requires the Earth to be a sphere when you don't have evidence for curvature. It requires evidence for space when the second law of thermodynamics destroys space. So you're making all these
I mean, this is
assumptions,
just.
and you're using the eclipses as proof of something when you need to make all these assumptions in order for it to work.
Eclipses are just one element. We also have many other things, which all come to the
Right.
Occam's razor solution of the shape of the Earth.
Including
Right. So what's
during the
what's
summer,
your
the
number
sun
one?
sets near the south in Australia, which you should know.
Right. So what's the number one best evidence say that the Earth is spinning?
Star trails, North and South Pole.
Wow. So we see the stars spinning. That means they're not spinning, and the Earth is spinning. No, that's
Yeah.
silly.
How about
Okay, look at it this way. You have those uncountable numbers of elements all in some sort of lockstep of motion to make the complete circles. Or we have the singular element of the rotation of the Earth.
No. So we have one star field turning above the Earth, and you're saying it's the globe spinning. Also, your globe is also orbiting and flying through space, and you're trying to use star trails, which are perfect circles and don't intersect, as proof of spin.
Yes.
No. So it could just be the stars spinning. So again,
Well,
there's a kinematic
the point-
equivalence with that. It could just be the stars spinning. Do you have any exclusive
Well,
evidence
the
that the
point
Earth is spinning?
the point being that the stars are an uncountable amount of elements, all in lockstep, moving at the various rates it takes to make the circles. So
Right. So that
that's
would
an unlikely
would
scenario. It's an unlikely scenario to have all that coordination with that many elements.
right. So then it would make a lot of sense if the stars were just spinning in lockstep together, which is what we observe. Correct?
No.
He missed
So
the
we
point.
don't.
I think he missed the point
So,
altogether.
You're
We have to have
assuming
an
they're
uncountable
different
amount of
elements.
points, an uncountable amount of points in lockstep, all moving at different speeds to make the circles,
different
or just the
they're moving at
singular
different
element of
speeds.
the Earth.
Okay. So your evidence that the Earth is spinning, again, is that we see the stars spinning, and therefore they're not spinning, and it's the Earth spinning. When relativity
lockstep-
says it could just be
In co-
the stars moving. Do you have any evidence exclusively that the Earth is spinning?
Yes, in concert with
What
that,
is
we have the variation in gravitational pull due to the centrifugal force of rotation. We have gyroscopic effects. We have all kinds of additional things coming together in concert.
So hang on, you say gravitational pull.
Sag effect.
Your gravity hasn't been a pull for 100 years. So you're like 100 years too late on that. Okay, it's not even a pull anymore in your own paradigm. So do you have any evidence of the Earth spinning that's exclusive to the globe?
Yeah, all the things I just stated, which you have no alternative for.
My alternative is with the stars are spinning.
So why do
Yeah,
you
we
weigh less
also-
at the equator than at the North Pole?
Why do what?
Why do you weigh less at the equator than at the North Pole?
Oh, do I? Wait, can you show me evidence for that? So you know that also in your current paradigm, therefore,
I'm saying that it's true. It's true. It's
been shown.
uncontrovertible.
That has been
Right.
shown that the variation of weight by latitude, which matches a quadratic for latitude. Yes.
Really? Okay. So gravity gets weaker as you get higher, correct?
Yes.
Yes.
Okay. So if I weigh myself on Mount Everest, do I weigh 1/3 of what I weighed at sea level?
Not 1/3.
Not
Oh no, it's not 1/3, but it is a measurable
Oh, it's
difference.
not. But the pressure is 1/3 less. But I don't weigh
that's air
1/3
pressure.
less.
We're talking about weight, not air pressure, because the buoyancy of your body would be a very, very, very tiny influence as well, but not in fractions the size of a third.
So can we measure it? If I go on top of Mount Everest, am I going to weigh less?
Yes.
Yes. Okay. Can you show me the evidence for that?
Oh God, it's been done so many
Nobody
times.
disputes it. What do you mean? Who even disputes that? It's just it's a well-known.
I've never seen evidence of that. I've never seen someone go on top of Mount Everest.
Okay, if you've never seen evidence, is that your requirement that only your own observations are valid and everything else by every industrialized country for centuries must be making shit up?
No, I'm just saying I've never seen evidence for it. Can you show me?
Yeah,
If I go
Critical
on-
Think
so if I
has done
go
the weight
search-
change with latitude experiment for like 5 years. Look up his channel,
So if
Critical
I go
Think.
search, hang on. So if I go search up, people weighing less on top of Mount Everest with scales, they're going to be going on top of Mount Everest and weighing themselves. I'm going to find heaps of videos of that.
No. Weight change with latitude.
How did you prove that latitude has anything to do with weight change? How did
It's
you
a
attribute that
prediction
to
of a
the Earth
rotating
spinning?
globe, Angel. It's a prediction
an
of a
observation.
rotating
Oh, okay.
globe.
Okay, so first of all, your exclusive evidence that the Earth is spinning is now weight change, correct?
I didn't say exclusive.
It was expressly pointed out. It's not exclusive of singular observation. It's in concert with all of them.
Well, I'm asking for exclusive evidence that the Earth is spinning. Like, if the Earth was spinning, it would have Coriolis, right?
Right. Do you have
Which it does.
evidence? Sorry, do you have a model that explains weight change with latitude? If you don't, then it is evidence of a rotating globe.
No, it's not. How did you isolate the rotating globe to prove that, Roohif?
No. What is evidence, Angel?
You're saying that this weight change happens due to the rotation of the Earth, but
Yes.
how did you isolate that to prove that?
Right. You can't prove anything in science, Angel. We've had this conversation.
Right. So then, holy shit! How did you verify that it's the Earth spinning that caused that weight change?
Right. You can't
It's the
prove
best
anything
explanation.
in science. You
I
can't
didn't
do
say
it.
prove. I said, how did you
did say
verify?
prove.
I said, how did you verify that the Earth spinning caused you to weigh less?
Right. It is a prediction of a rotating globe.
But you did. Okay, so you don't have actual evidence or verification
It
that
is
it's
evidence.
because of the spinning.
Right.
So
You can't
how
prove
did you-
anything in
okay,
science, Angel. I'll say the same
but then
fucking
how
thing
did you
over and over
verify-
again.
Then how did you verify that it was
By
the Earth
repeatable
spinning that
measurement.
caused that?
By
Right. When you
repeatable
say
measurement.
verify, you mean prove, don't you? What do you mean if it's not proved?
Roohif, did science prove that water could boil at a sea
No,
level at a
science
certain
doesn't
temperature?
prove
No, it
things.
didn't. So science didn't prove that water boils at a certain temperature.
No, that's a measurement, Angel. It's a measurement of the temperature.
So
Not a proof of the theory.
Yes, it is.
No, it's not. You can't prove an explanation of that reality.
Hang on. So it's not proven that water boils at a certain temperature at sea level. It's not proven.
That's not a proof, Angel. That is a measurement of the temperature. Right? It's a measurement. That's a fact. Right? That's a fact that it boils at 100 degrees.
Okay.
Right? Proof of a theory.
How about we do this a different way? If the Earth is spinning, right, do you guys agree it would have Coriolis?
Yes.
Okay. So measurable Coriolis, correct?
Yep. It is evident in the cyclones and hurricanes.
Okay. So if I let go of a helium balloon on the Earth, does the Earth rotate under it?
Jesus Christ. You're aware of conservation of momentum, right?
Right. So now the thing that's meant to be proving we're turning doesn't happen now.
No. You've got a fucking child's understanding of what Coriolis is.
What's the Coriolis formula?
Conservation of momentum. Oh,
what's the Coriolis formula? So why do you say that I don't know it? Okay, so then why do you say I don't understand Coriolis then?
Because what you're trying to say is that if I let go of a helium balloon, the Earth is going to whiz past at 1,000 miles an hour, and the balloon's going to end up thousands of miles somewhere else. Correct?
No. What you said is the Earth has Coriolis. What you said is the Earth has Coriolis, which means there's an apparent deflection of an object in the atmosphere. Correct?
Yep.
Yeah, which there is. You can look up King of 2 Miles, and you can see that they all do a Coriolis correction.
Right. And when I let go of a helium balloon,
in their ballistic solution, they all use a Coriolis correction.
Oh, okay. So in ballistics, they use Coriolis correction. So sniper has to account for Coriolis. Yes.
Go back to your helium balloon. Back to your helium balloon. You let go of a helium balloon. What do you think should happen?
Nothing, because the Earth is stationary.
No, on a rotating globe, what should happen to that helium balloon?
That's a burden of proof reversal fallacy. I don't believe the Earth has Coriolis.
What was your helium balloon example?
That's for you to answer. Actually,
so why'd you bring it up then? So why did you bring it up?
Because that's what I asked you. So you said the Earth has Coriolis, but then when I said does it rotate under the helium balloon, you said no.
Well,
that's not
Coriolis.
It
does, but how much? Technically, it does, but how much? Yeah, how much?
Can you show me the evidence? Can you show me the evidence for someone letting go a helium balloon and seeing Coriolis deflection on it?
It's not my example. It's not how I demonstrate Coriolis. Coriolis is evident in cyclones and hurricanes, not helium balloons.
So it's evident. So it's evident in cyclones and hurricanes, but snipers have to adjust for it.
Yeah, I mean it's evident. It's evident, obviously, in ballistics, where you have a heavy projectile in which the inertial forces exceed the drag forces, such that you can see the apparent deflection. Obviously, in the case of a balloon, the inertial forces are tiny compared to the aerodynamic forces. So the aerodynamic forces are going to dominate it.
Okay. So
you brought up the helium balloon, Angel. Why? Why did you bring up the helium balloon? What is your point?
Because if you let go of a helium balloon, it increases tangential velocity to the Earth. It does it not?
How much?
It doesn't matter how much, does it?
Yes, it does.
Okay. So then does it increase? So then does it? Hang on. Does it increase tangential velocity to keep up with the Earth, or does it lag behind you and have a Coriolis?
Well, it just gets blown around by the wind.
The atmosphere is far too complicated to try to isolate it in that example.
Yeah, because like I said,
how much, Angel? How much?
When the aerodynamic forces work, the inertial forces, you're not going to be able to make a measurement.
So Roohif, you said how much. Why are you asking me how much? I'm asking you that.
Right, because I say that the wind is a far, far greater factor than Coriolis. Right? Coriolis is negligible.
I'm not talking about wind. You just said I'm only talking about. That's for you to tell me, Roohif.
We have to include wind. We have to include wind.
Okay, so
the only reason why the balloon is flying is because it's in an atmosphere. That's the only reason why it's flying and gaining altitude, right? And that atmosphere and that balloon is going to move whichever way the atmosphere is moving.
Okay, great. So how did you isolate and prove, or how did you verify that the Earth rotated under the balloon when you let go of it?
Don't use a balloon for it, Angels. I've said it's evident in cyclones and hurricanes. not a fucking
Okay,
helium
so
balloon.
if the Earth rotates under a cyclone and under a hurricane, does it rotate under everything else, or just that?
Yes, it rotates in objects in which their inertial rotates in objects in which the inertial forces
the atmosphere rotates with the Earth.
So there's no correlations then. If the atmosphere moves with the Earth now.
You're such a disingenuous fuck, Angel. Seriously.
No, I'm not. Roohif, why are you swearing at me?
Because you're a disingenuous fuck.
If I'm disingenuous, Roohif, how many reference frames does Coriolis need?
Oh, Jesus. Okay. We've had this conversation before as well.
Yeah, I know we did.
There's an inertial reference frame and a rotating reference frame.
Right. So
there's a
then
rotating reference
Coriolis
frame
needs
and an
two.
inertial reference frame.
So
Right.
Coriolis needs 2 reference frames, correct?
Yeah, we've had this conversation. Yep.
Yeah. Okay. So when the balloon's in the air, is it in a separate reference frame now?
All objects. This is exactly what I said to you, 6 months ago, whenever it was.
Here we go.
All objects
Okay.
exist in all reference frames at all times. It's not the
Okay,
case
so when
a balloon is in one reference frame and not in another. That is a fucking child's understanding of reference.
Wait. Okay, so I'm holding the balloon and I let it go. It's in the balloon's in the air now. You just said it's in all reference frames at all times. So while the balloon is in the air, I'm still holding it, am I?
No. Do you know what a reference frame is? Clearly not.
Yeah,
You've learned nothing in the last 2 years.
I don't. You just said the balloon is in all reference frames at all times. Yes.
Yes.
You can
So
think
when
of
I'm
it like
holding it,
camera.
is it-
You can think of it like camera angles. You could have a camera angle on the ground. You could have a camera angle on the balloon.
That's a good analogy.
Yeah. So when I'm holding the balloon, is it in a reference frame on the Earth attached to me?
Objects.
Yes, you
listen
cannot.
to me.
No element can leave a reference frame.
Oh, so
A reference
you can't leave the
frame
Earth
is an
now. You can't go
observer
to space.
position. A reference frame is an observer position. Okay, you have
Okay, so
two
when I'm
observers
observing the Earth,
looking at the same scene. All right.
okay, so when I'm looking at the balloon going up away from the Earth, okay, and it's increasing tangential velocity to the Earth, does it keep up with the Earth?
It's
Yes, it is. Are you joking?
No, it's not.
It's not. When a helium balloon rises up in the air on a globe, is it increasing radius value to that globe?
Yes, that doesn't mean the balloon catches up.
And
No, I'm saying it would have to
the
increase
balloon is
tangential
still this balloon is still being driven by the wind. So whatever the wind is doing is what the balloon is doing.
So the atmosphere moves with the Earth, is what you guys are saying. So then, if I put if I put a plane flying at the equator west against the rotation of the Earth, how come it doesn't have 1,000-mile-an-hour headwind? If the air moves with the Earth,
Did you just fucking listen to what you just said? Seriously.
Yeah, he did.
Yeah.
We just said
Okay,
the atmosphere
Yeah.
moves with the Earth. Did we not just say the atmosphere moves with the Earth?
Right. At what speed at the equator, Roohif?
Relative to an inertial reference frame, 1,000 miles an hour.
Yeah. Okay. So the air is moving with the Earth 1,000 miles an hour at the equator east.
Yes.
If I fly against that, do I have 1,000-mile-an-hour headwind?
No.
No, because the atmosphere moves with the fucking Earth. You are one of the stupidest flat earthers I've ever met, Angel, and one of the most arrogant.
Just like it would be on,
it's
just
insane.
like it would be on a stationary Earth. So hang on a
because he
second.
grew up
So
on
the atmosphere moves with the Earth 1,000 miles an hour. But if I fly against it, there's no air moving towards me, Roohif.
Because of momentum.
Correct.
The conservation.
When you're on the ramp, when the aircraft is on the ramp, it has that same 1,000-mile-an-hour eastward velocity, and as it departs the ground, it remains in that same reference frame and still retains its 1,000-mile-an-hour eastward tangential velocity.
Right.
And if it goes into the wind, it's the wind and the plane still headed to the initial 1,000 miles an hour. Yeah,
Yes.
nothing is lost.
But I'm not talking about flying east with the rotation. I'm talking about flying against it. If you guys are going to
that's what I said. Yeah, takes off and flies west. Nothing has changed. It still had that eastward 1,000 miles an hour while on the ramp, and as it takes off, it doesn't lose that.
Wait. So the atmosphere.
Can we just
So the
can I ask
atmosphere moves. Oh my gosh!
Just want to ask the question. Move the goalpost a little bit. So when we say the Earth, right, and we say that the same like reference frames or when it leaves the ground? Can we just be a little more specific with what do you mean by the Earth? Whoever's asking, and Roohif, do you consider the Earth just the ground or the whole entire system together? And if it's one system, then if you are going from a solid surface to a non-solid atmosphere, how is that one system? I understand reference frame, but Earth and sky are two separate mediums. So can we just
exactly?
But is that a reference frame question?
Well, it's
No,
both. Reference frame for you, and yeah.
Okay, but do you understand what reference frames are?
No,
Well,
just answer the question.
I don't want to play
Roohif.
that game.
Ask your question.
I want to talk about mediums as well. Reference frame, then mediums. Yeah.
Okay. The Earth, if you include the atmosphere, I'm happy to say that's one system.
Okay, so then how many systems reference frames does Coriolis need again? 2. So you've combined them, so there's no Coriolis on the Earth when
Holy
you combine
shit!
them. Thanks.
You've done it again. What you're saying,
What did I do
Angel?
again?
You're saying that
Yeah.
the atmosphere is a reference frame and the Earth is a different reference frame. Objects, right, are not reference frames. They're observer positions.
Okay. So again, okay, the Earth itself, okay, which is rotating, okay, without the atmos, let's just remove that for now. Is that a reference frame when we're standing on
You
it?
can say my reference frame is an observer rotating with the Earth, and sometimes we shorthand that to say the Earth's reference frame, right? Or you can say
Right.
an
How many-
inertial reference frame with respect to the stars. They exist at the same time.
Okay. If I hover a helicopter in relation to the fixed stars, does the Earth rotate underneath us?
Yeah, if you're stationary with respect to the fixed stars, then yes, the Earth will rotate relative to that. Yes.
Wait. So the world record helicopter hover was over 50 hours, and they landed back in the same spot.
Was it
They landed
stationary
back in
with
the same
respect
spot.
to the stars, you fucking muppet?
Yes. Yeah.
No, it wasn't.
I don't know why.
Jesus Christ.
But wait, they were
Stationary
adjusting
relative
for
to the
Coriolis.
Earth. If you ever hovered a
they were-
helicopter, it's not easy
wait,
thing
they
to
were-
do. You're flying the damn airplane relative to keeping in the same position.
So they were adjusting for Coriolis the whole time, is your argument?
No, they were just
No, they were-
hovering in a spot. They were not stationary with respect to the stars. They were
They were
stationary
hovering
with
to
respect
stay
to
in
the Earth.
position.
So wait, you're telling me if they mentally decided that they're hovering in relation to the stars, the Earth's
How
going
would
to
they do
rotate
that?
underneath?
Not how do they don't mentally decide it? They fly westwards at a fucking 1,000 miles an hour. That's how they would do it.
In a
I'm only
helicopter,
talking
yeah,
hovering.
that'd be a trick. That'd be a real trick.
Hovering in one spot. Hovering in one
Right.
spot.
So they're not stationary with respect to the stars. They're not
So if
stationary
they,
with
if they
respect
had
to
a,
the stars.
so if it was nighttime and they were underneath a star, right, zenith to it, and they stayed stationary relative to that star, would the Earth rotate underneath the helicopter?
Yeah, because they'd be flying westwards at 1,000 miles an hour. If they're following the GP of that star, right, they're flying west at 1,000 miles an hour at the equator.
Whoa! So the Earth rotates on the hovering helicopter.
Oh, holy fuck! You're the most disingenuous and stupid fuck I've ever met,
hovering.
Angel.
If it's following
You're not
the
hovering if
star
you're flying
position, it's not
1,000
hovering.
miles per hour westbound.
Dude, you're getting angry because you're just fucking. Oh, this is so
No, I'm getting
embarrassing.
angry because you
You're
cannot
just a
be this
dishonest
dumb.
fuck.
You really cannot be
Yeah.
this
Well,
dumb.
he can.
Roohif, what am I
He is
being
both
dishonest
stupid
about?
and a fuckwit.
Hang on, Roohif, you're swearing at me because you're losing very badly. Okay.
No,
Tell
he's
everybody.
not. He's really not.
Tell everybody how I'm disingenuous in what I'm saying right now.
Oh, either you're incredibly stupid or you intentionally misunderstand what I'm saying.
Okay, I
Which
just
of
asked
those
you.
is correct?
I just asked you if the helicopter is hovering in relation to the stars, which are not moving in your paradigm. You said the Earth's going to rotate under it. Is that correct?
Yes. Yes. And to
So
do
when-
that,
so
you
then
need
when
to
I-
fly westward at 1,000 miles an hour.
So you're telling me that the pilots are also going to be adjusting for Coriolis then?
No.
No.
No. If you want to remain stationary with respect to the stars, You need to counteract the rotation, which means flying west.
Which means they would have to move the fucking helicopter, yes?
Right. So you're not hovering.
So yes, they do have to adjust for Coriolis now.
No, they don't. That's not Coriolis.
Oh my god. Oh,
Jesus.
This is so funny, dude. Wait. So, Roohif. So, when you're standing on the Earth on a field, is your head moving faster than your feet?
Technically, yes.
Okay. So, when you're lying, you're in Australia, right? Now?
Yep.
Okay, if you lie down with your head facing north, is your head moving faster than your feet?
Tangentially, yes.
Right. So then if your head is moving faster than your feet in both examples and you throw a ball up, does the ball increase tangential velocity to keep up with the Earth, or does it lag behind?
No.
And have a
Lags.
Coriolis? So if I throw a ball up, the Earth's going to rotate under it.
How far can you throw a
Very
ball?
minuscule. Very, very minuscule amount, but yes.
Can you show me evidence of that? Someone's throwing up a
It's
ball.
not
and the
my
Earth rotates.
fucking claim. It's not. I did not at any stage say I had evidence of that. I have said many times the evidence of Coriolis is in cyclones and hurricanes.
You'd be one
This
hell
is
of a
why you're a disingenuous fuck angel.
You could be one hell of a cricket player or a baseball player if you could throw a ball that high, that you can observe that
Roohif,
difference.
did we not? Hang on. Did we not all hear Roohif just say that when someone throws up a ball, the Earth rotates under it? That's what he just said.
Yes, we all
By
agree
a
with him.
minuscule amount. By a
Okay,
minuscule
so then
amount.
could you show me the evidence? Okay, so then could you show
I
me?
didn't
evidence?
claim that
yes.
I had evidence of it.
Angel, if you're
So you
going to
just
do
claim
this,
it
you're going to
yourself.
have to plug in the equation, the RPMs or the amount of rotation, and the amount of rotation is 0.000694 RPM.
So okay, so if we're at the equator,
the difference between what 3,000 miles and 3,000 miles and 10 feet that you threw up in the air, it's like nothing.
Is it measurable?
It's nothing.
Is it measurable?
No, not
Is it
measurable.
measurable?
No, probably not.
No, the
No.
evidence for
So now
fucking
the- so now the
Coriolis
Earth doesn't-
is in
now the Earth
hurricanes and
doesn't rotate.
cyclones.
Wait, Roohif,
Oh,
so you just said no now. So the Earth
difference.
doesn't rotate under the pole now.
The difference between
No, I said, hang on, NASA. I said the measurement of throwing a ball up in the air is far too minuscule to measure. The evidence for
So you can't
Coriolis
measure
is
it.
cyclones and hurricanes.
Okay, so then
think
can you agree that throwing up a ball on a stationary
Hang
Earth
on,
is what
RG.
we observe?
Hang on, RG, what'd you say?
Oh, I think what I'm hearing is like, I think, so the big differences or the big takeaways, of Coriolis from what I'm hearing you say, Roohif, and is a visual measurement in cyclones and hurricanes, basically, because you're able to see the spinning or turning, and this is the Coriolis that you're mentioning. I think now measurement mathematically could be different with, your feet in your head being different, or 100 miles up in the atmosphere and the ground, like it's going to be measurably Coriolis. Is kind of what I'm hearing. Is that the big differences in
the amount, like when Angel goes, throw a ball in the air, will it lag behind? Yes, it will, but the measurable amount,
it's not measurable.
There's no way you could measure it. It's just
So
too
there's
small.
no way you could measure it. Wait, hang on a second, Roohif. There's no way you could measure it. So how do you know what's happening?
I don't claim that I have evidence of throwing a ball in the air and it moving a tenth of a millimeter. I never said that. I said for the fifth time, Angel, the evidence for Coriolis is cyclones and hurricanes, and you refuse to address that.
But to be clear, in very precise drop tower tests, it has been measured.
Okay, wait, Roohif, you just said that it's not measurable, yet you're saying it happens. So if it's not measurable,
Jesus, this is why. Can everyone see how much of a disingenuous fuck he is?
No, yeah, it's.
But wait, hang on, we haven't moved. Dude, I'm asking you a question. Right? You just said yes, it rotates under it. No, it's not measurable. That's a contradiction, right?
With a baseball.
Throwing the ball in the air, the amount that it would lag behind is too small to measure. Therefore, it's not something I use as evidence. So the evidence I do use is, what's the evidence I do use, Angel?
Yeah, cyclones or whatever you said. But if you are going to claim, that the Earth rotates under a cyclone, which it does, it, Roohif?
Yeah.
Oh, it does.
As
So
the pocket of air moves north.
Okay, so is the cyclone freely able to move over the Earth?
It's wind. Yeah, wind moves over the Earth, right?
Okay, so how come it doesn't just magically tether with the Earth and like all the other examples I'm giving you, like the helicopter?
Because its helicopter is being flown by a pilot. The hurricane is not.
Yeah.
It's
what about the
effectively a
helium balloon?
ballistic.
What about the helium balloon? That
What
has been
about the helium balloon?
so
Unlike the
does the
hovering
helium balloon
heli-
move with the Earth? Does the helium balloon move with the Earth?
Yes. If you're on the
So how
ground
come-
in
so-
fucking Melbourne, whatever, 500 miles an hour, you let it go from the inertial reference
I mean,
frame.
this
Yes,
guy's-
that balloon's
this guy's
moving
a-
500 miles an hour.
This guy's a Southern Hemisphere flat earther?
So then does the
Yes.
so then does the cyclone move with the Earth, or is it able to freely move over the Earth?
Yeah, air moves over the Earth. It's wind. You're aware of wind,
so
right?
right. So then wind is not Coriolis. Then you know that, right?
Jesus Christ.
You know wind is not Coriolis, really. Is wind Coriolis?
Are you really a Southern Hemisphere flat earther?
I'm actually in America now, and so yeah.
Look, the jet stream. The jet stream. Regular wind is not Coriolis, but the jet stream is Coriolis.
Wait, jet streams and
the
trade
jet
winds going
streams are
opposite
caused
directions.
by Coriolis, yeah.
What? Roohif, so do you know what? So jet streams go one way, east or west. One of them.
No, some go west
And,
east.
trade winds go the opposite
west-east.
directions.
All,
And trade winds go the opposite directions. So how do trade winds and jet streams go in opposite directions on the globe? If it's all
it is
caused by
a
Coriolis
big-
going one way.
Hadley
It is a
cells.
big
Look up
circular
Hadley cells.
thing.
What?
Look up Hadley cells and come back later.
Yeah, the
Look
jet
up your
stream thing is a
evidence.
whole 3D circular thing.
Okay,
It's
so
a good diagram. Yeah.
so jet streams and trade winds go in opposite directions, though.
Cool.
You understand that, right? Okay, but the globe goes in
3D.
one direction.
Right.
Right. So if the globe is only spinning one direction, how do you have things going in opposite directions?
Hadley cells. Look up Hadley cells and come back, okay?
Yeah. There's a
Hadley
good
cell. What
diagram
is
out
Hadley
there.
cell?
Look,
There's
if
a
you don't
good
know what Hadley
diagram
cells
like
are,
a-
then you shouldn't be doing this.
What do you have?
That's not an
Explain
argument.
it to me.
Tell someone to go Google something, dude. Just don't even
Exactly.
put that on the live stream.
Explain
if
it
you
to
have
me.
to say your thing. Don't just tell people to go Google stuff. That's not why we're
You
here.
have to Google stuff because explaining Hadley cells is difficult. It's a three-dimensional
so if
process.
Well, then don't make the
This
argument.
guy-
You can't explain
This guy has shown that he can
Okay.
do
Explain it
everything
to me.
in 2 dimensions.
Wait. So let me look. Okay. Do snipers have to take the Coriolis into account? Yes or no?
Super long distance ones, like the best, like think of 2 miles where they're shooting 2 miles. Yes.
Okay. Does the Earth rotate under a hovering? Does
According to the military,
Earth rotate?
if they can see the
All right,
target, they don't take it into account, according to the military.
We've answered
Alright,
this,
That's
Angel.
what they have in-
He said yes, right? They have to take it into account. Whatever. Does the
Yeah,
Earth
you can
rotate
talk.
under
You
a
can talk to
hovering?
the competitors. They all use Coriolis in their ballistic solution.
All right. Which formula do they use for that, bud? Which Coriolis formula do they use?
It's whatever's used in the ballistic calculator.
Oh, which one though? You're making a
doesn't matter.
positive claim that they take
What do
into
you
account.
mean?
What formula do they use? Which
I don't
Coriolis formula
know.
do they use?
I don't know. Most of them use the Kestrel ballistic calculator. I guess you can send an email to Kestrel and ask them.
All right. So, does the Earth rotate under a hovering hot air balloon?
We've been through this.
Oh, a
It doesn't.
hot air
It's
balloon.
minuscule.
Oh, that's way different than a helium balloon.
Okay. So if we put the sniper in the hot air, wait. If we put the sniper in the hot air balloon and
Jesus.
takes a shot. Jeez.
You know,
So
I was at a
posted
balloon launch. I
American
was at a
Shooting
balloon launch the
Journal.
other day. I was at a balloon launch the other day, and as soon as the balloons broke the ground, they were going eastbound at 700 miles per hour. That was pretty amazing.
Hey, I love you guys, man. Hey, I love you guys. You think that? If not, but just answer my question, right? If the sniper's in the hot air balloon, and he takes the shot. Are you trying to tell me that it will rotate under the bullet, but not the balloon he's in?
Fuck's sake. For fuck's sake.
No, that's not what we're
For
trying
fuck's
to
sake.
say. Did
And
you
then what
look
happens?
at look at what I posted in the chat? There's the American Shooting Journal describes how precision long range shooting is affected by the Coriolis effect, and they have nothing to do with the flat Earth of globe Earth debate. They're just talking about precision long range shooting. So should we call them up and tell them to delete all their stuff because it's all wrong?
Yeah, I'd love to know what Coriolis formula they used, actually. Yeah.
Then
Yeah,
ask them.
There's
You're like a
ballistics
math teacher,
calculators.
right? You're a math teacher, though,
So
right?
does
Matthew?
so when a sniper
So
a
if you
sniper
do
in
the
war, right?
if you do the
A
math,
sniper in war,
just go.
a sniper in war has a compass on his gun, and he has to manually calculate Coriolis before he takes a shot. Is that what you're trying to tell me?
Yeah, they're not
No, they
usually not
usually use
shooting
the
targets out 2
calculator.
miles out. Yeah, they're not shooting their targets 2 miles out.
So let me ask you guys a question, right? Let's say we were 2 miles away from each other. We both had a sniper rifle, and we were aiming at each other. You had to calculate for Coriolis before you take your shot, and I didn't. Would you do that with me?
Yeah, you lose.
Yeah, 2 miles is probably
I'd lose.
enough to make a difference.
I'd take 5 shots before you calculate, though.
No, you wouldn't.
That's just stupid.
I know a lot of people take in when into
Yeah, in the old
have you ever been hunting and you're
in the old
shoot something kind of long range, but you have to click your little adjuster there up or down or left or right. I know that kind of thing, but I don't know if it's called Coriolis in that manner. I just know that if there is a crosswind, you'll definitely miss your target if you don't adjust. But my bigger question is to, I guess, both globe and flat earthers. So does anyone know for sure or can point me in a direction that the higher an elevation you get toward the crosswinds of, we know that weather patterns at certain heights and are a lot stronger. So as you go up in altitude, I know you're gonna move quicker in one direction or the other, right? Does anyone
like in the jet streams? Yeah.
Yeah, for
I
the
have
jet
that data.
stream. All right. So that we know for sure then as you go up, you're going to move quicker out from, is it necessarily out from under you or just pushing the object one way or the other? Who would want to answer that? Right.
Yeah,
That's what that's my
jet
guess.
streams are strong winds.
Right.
What do you say? Pulling out from underneath you or something? What was that?
Yeah, is that what you would say? Is that as you go up in elevation, you would go faster one way or the other, or would you just say it's the Earth moving under you quicker or something?
It's being in a wind. Like if you're a balloon in a wind, you're moving like 100 miles an hour, whatever.
Right now, let's say a big helicopter or a light helicopter, or let's not go with airplanes. Let's say if you go up in elevation in a helicopter, would you move quicker because of the winds as well?
Yes.
Okay.
Wait, I got a question here, right? I got a good question. So you guys agree turning is acceleration, right? Okay, you can look this up, but turning is acceleration, and acceleration requires extra energy. So when a hovering helicopter moves with the Earth, okay, let's say for a 24-hour hover, it's done a full circle in space. Like, let's say you have a satellite really far away from the Earth. You see the Earth spinning, and the helicopter would be spinning with it in a circle, correct?
Yeah, but helicopters don't care about that. All they care about is their ground speed when they're hovering. They're just flying relative.
My
to
question is, that's not my question. Does the helicopter spin with the Earth? And if you were to see it from the outside, the helicopter would do a circle.
Yeah, if it's hovering over one spot, it would be spinning with the Earth, obviously.
Okay, and it'll be doing a circle, right? In the air?
I mean, if it hovered for 24 hours, then yeah, it would be doing a circle from an outside viewer's perspective.
Okay, so turning is acceleration, which requires extra energy. What magical force is pulling it and making it change directions constantly?
The pilot is flying the helicopter relative to
So the pilot's making the adjusting for curve as well while hovering?
No.
Yeah, there's a balance. There's a balance of forces between the gravity that's pulling the helicopter down and the lift that the helicopter's blades are creating. In the same way that when a car goes through a corner, there's a balance of forces of it of its inertia trying to drag it out into a line, and the car's tires providing the grip that are trying to keep it in line.
Turning at a constant rate is acceleration. Acceleration requires extra energy to happen.
So the tops of the trees need energies. The tops of the trees, the tops of the trees need energy to hold up with the bottom of the trees, right? Because they're taller.
Dude, the trees that are firmly planted into the ground.
Right,
okay, they're
right.
not attached to the earth. Wait,
so
the hovering helicopter is attached to the
the
earth.
helicopter is no different than if it was on a pole. It's just being flown.
What?
Yeah. So are you trying to tell me? So then are you trying to tell me that like on a tether ball, if I throw a tether ball and then it has to do a full 360 circle and come back at me, which it travels like 10 feet, that it takes more energy for it to do that than to just throw the ball 10 feet? Is that what you're saying?
Wait. I'm not talking about a tether ball. Okay, I'm talking about something changing directions constantly. That's not tethered by anything.
Yeah.
Is the
A tether
helicopter
ball.
tethered?
Yeah, the helicopter is tethered. The helicopter is tethered by gravity, which is trying to pull the helicopter down just the same way, in the same way that the tether on the tether ball is trying to keep the ball from traveling in a straight path.
Wait. So clouds that move in all directions are
Now we're going to clouds. Can you change to a topic? So you have to switch from clouds to guns, to helicopters. Yes, you are. It's like a scattershot.
I know. It's literally, it's just scattergunning.
This is not me changing topic. You said
You've changed from helicopters to balloons to guns to clouds to what else? Wind to you keep on like boo 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 boo. You can't take on one topic.
Watch this. It is on the same topic. So
no,
you're saying that the helicopter's tethered to the Earth, and the Earth only spins one direction. Therefore, the helicopter is only moving one direction. Correct?
It's as if it was on a pole. What would be the difference?
Okay, so when clouds are above the Earth and they move in all directions, are they also tethered to the Earth by gravity?
Yes, they're still tethered by the Earth by gravity.
Oh, but so they're tethered to the Earth by gravity, but they can move the opposite direction of the Earth spin.
Because winds, yes, wind. We know about winds.
Right.
We know about wind.
I don't want to use the R word.
When you talk about this, being in when the atmosphere being in lockstep, most sorta. But the difference between the atmosphere and the ground, we call that difference. Wait for it. Wind.
Wait, what? Dude, hang on. As you go higher up in the atmos, the clouds and all the
what the hell's an atmos? What do you mean? What's an atmos?
Air. You don't know
the
what
atmosphere.
Means?
The atmosphere. Thank you.
Well, hang on a second. Atmosphere is a contradiction in terms. Atmos means air. Sphere is a shape. Air doesn't take the shape. It doesn't have inherent shape. It takes on the shape.
Atmosphere. That's the word. I've never seen the word atmos in any book besides. So we can talk atmosphere.
Wow.
So the atmosphere. Okay.
So the atmos. Okay.
Atmosphere.
Needs a container. It needs a container to take
the
shape of a sphere.
No, it doesn't.
Oh, really? So do gases take on inherent shapes on their own?
Again, there's this force called gravity that's pulling it all together.
Gravity is not a force in your current paradigm. You're 100 years too late.
Thank you.
No, it's not. It's the bending and warping. It's the bending and warping of the force.
We don't want to talk about space-time, the fact that the Earth bends.
I know, because you don't know your own globe.
Fade, you can't, this guy can't steel man his own model. We went through this last night. This guy can't steel man his own model.
This guy is changing
your model at every turn.
Now comes in the cavalry. The White Knight cavalry comes in.
Wait, Jeremy,
the guy called it. The guy called it. You straw man in your own model at every turn.
Okay, thank you for that, NASA Shill. Now, you said that the helicopters tethered to the Earth and moves one direction with the Earth, but clouds are also tethered to the Earth, but they can move in all directions.
Because of wind.
You know that's a contradiction. You know that's a contradiction in terms, right?
Nope, it's not. Sorry.
Okay, so then if the clouds are tethered to the
pilot
Earth,
is actively flying the airplane to stay in one position.
Oh, so now it's the pilot that's tethering it to the Earth, not gravity.
Well, no, the pilot's tethering it left, right, up and down. Yeah. Because he's flying. Gravity's pulling down. Those little whirly things on top. You know those little whirly things on top? Yeah, for this
Gravity's not
demonstration,
a
we'll
pull
talk
in the
about.
current paradigm.
For this time, we'll talk about Newtonian gravity since it's easier to analyze on a
Which
helicopter.
has been superseded by Einsteinian, which you don't know.
Nope, has been superseded. Sorry, it's been.
Yes, it has.
Phil, can I ask you, at what point does gravity
Again,
stop pulling or pushing? Like
we're
at
going to
what
talk
pressure,
Newtonian
at like
gravity.
your PSI type of what you're speaking of, like at what point, right, between the upper atmosphere and the ground does gravity stop pushing or
Doesn't.
pulling?
You understand? There's a
It
gradient
doesn't.
in the atmosphere.
So if it doesn't,
You know,
if it doesn't
there's a
pull at the
gradient of
end,
atmosphere. You know, there's a
if it
gradient
doesn't
in the
pull,
atmosphere, right?
then okay. If it's a gradient,
You
right?
know, you can demonstrate this gradient. Do you have a cell phone?
altitude?
Do you have a
At
cell
what
phone?
altitude?
Do you have a cell phone?
Can you stop that, Shill? You're literally just being obtuse now.
Do you have a cell phone? No, we're going to talk about the gradient. Do you have a cell phone? You can demonstrate the
I'm
gradient with
just
your cell
asking
phone.
a simple question. Like, at what
trying to ask
point
you a question.
does it stop pulling things to
doesn't.
the ground?
It doesn't.
It doesn't. So why is it indifferent to bees or butterflies versus helicopters and clouds?
Because bees and helicopters spend a shitload of energy to oppose gravity.
Okay, that's not very scientific. I'm just
Yeah, it is.
trying to be
Actually.
specific.
It's very scientific. They're
I want to ask him a
expending
question, right?
energy against the atmosphere to hold themselves up in the air.
That's
Okay,
for sure.
so now gravity doesn't pull, it holds things in the air.
Now gravity pulls things downward. Thank you.
Okay,
Yeah,
that sounds pretty
paradigm,
legitimate.
dude.
That's why
Go
there's a
ahead, guys.
gradient. The gradient in the atmosphere. You can demonstrate this gradient with a cell phone.
Okay, fair enough.
You don't believe?
Okay. What are the two things that change air pressure, NASA Shill?
You tell me what you're going for.
Well, can you tell? Do you know? Like, I can tell you, but do you know what are the two things that can change gas
Why don't
pressure?
you tell me? I want to know what you're going for. Oh, we're not talking about gas pressure. We're talking about atmospheric. We're talking about atmospheric pressure. That's different.
You're one of those globies. No, you're one of those.
Atmospheric pressure.
What is the atmos made out of? What is the atmos made out of?
We're talking about atmospheric pressure, though. It's like the water. Have you been in a pool and dove down to the bottom and noticed the increase in pressure? Yeah.
It's when I breathe. Am I drinking?
Then again, when you dive in the pool and you go to the bottom, I don't know, say 10 feet, you feel that pressure on your ears. What causes that?
Yeah, probably because there's a lot more water above you.
Wait, well, more water above you. Very good. So that's the same reason that there's more pressure. It's the weight of the air above you. Exactly. Thank you for the analogy. You said it correctly for a change. I'll agree with you one time. Excuse me. I would like everyone to notice that I actually agreed with you once today that the pressure at the bottom of the pool is caused by the weight of the water above you.
Bro. You're an attention whore, bro. Chill out.
Excuse me. I just want everyone to know that I don't totally disagree with this guy. That we actually agreed once.
Okay. All right. Thank you. We heard you the first time.
So now that's the same thing that happens in the atmosphere.
Okay, great. So you're saying that the atmosphere, okay, as you go higher, it gets thinner and thinner, correct? Due to gravity?
That's correct.
Okay. Does the Earth have an ozone layer?
What's that got to do with anything?
Yes or no? Does the Earth have an ozone layer?
What does that have to do with anything?
Just answer. Okay, so the Earth has an ozone layer that's higher up in the atmosphere, according to you. You just said as you go higher, the gas gets thinner and thinner. Ozone is more dense than air. So how come the ozone layer is not on the floor?
Because ozone is a very unstable chemical.
Chemical, dude, it's a gas.
Atmosphere.
So
ozone is a very unstable chemical.
It's not a chemical; it's a gas.
What
so
do you
as
think
you go higher up,
are?
you said the gas.
What do you think chemicals are?
You said the gases get thinner as you go higher, but the ozone layer is not on the ground. That's more dense than oxygen. So how does that work?
Ozone is a very unstable gas molecule.
Dude, that doesn't answer the question. That's literally an ad hoc explanation.
No, it's not. It's exactly the explanation. You don't.
Explain how it. Explain
That's
how
not
it
we
being
talking
unstable.
to ozone now. You don't understand ozone now.
Explain
This is
how
the first one I've
ozone
heard.
gas. Explain how ozone gas, which is more dense than oxygen, is up in the atmosphere when you said it would thin out.
How do you make ozone? Do you know why ozone is up in the atmosphere? You know that?
Can you just answer my question?
Well, no, you have to tell me why ozone is there in the first place.
This guy has no clue, Angel. He has no clue, bro.
I have plenty of clues. You don't, obviously.
Well,
Take gravity
wait,
makes
no,
Chill happy.
Let me ask you a
No, it's
question,
not
right,
actually.
Phil?
It's
Okay.
not
If
quite.
we put like 5 different density gases in a really big container, will they layer out? Or will they mix? Will the particles mix together and just randomly move in all directions?
How big is your container?
It doesn't matter, whatever size you want.
Yeah, it does.
Will the gas particles
Actually, it
mix
does.
together?
The world.
Actually, it does
Will
matter.
the gas particles mix together?
How big is your container?
5 liters. Will the gas particles mix together?
5 liters, yes.
Oh, okay. So if gases don't layer out, how do you have an ozone layer?
You said we're talking 5 liters, so you go from 5-liter container now to the entire Earth system. That's and say that they're both the same because the 5 liters will happen on the Earth with the big massive Earth in the middle of this. Yeah, so
hang on a second.
that's exactly. So they're exactly the same according to you. Yeah.
So gases move.
Wow.
Gases
I guess your little toy truck and like a big a big dump truck are exactly the same thing,
I'm
right?
being
Because they're both
sarcastic.
trucks.
Come on, bro.
No, it's exactly
So
what he's
gases-
done. He's compared a 5-liter container to the Earth
Yeah,
system.
I'll tell you this. Look.
Fuck's
Either
sake.
way, bro. The jet streams and the weather system are gonna mix everything up anyway. So you got to face that.
How high up is the ozone
There's no
layer?
true gradient on.
How high up is the ozone layer?
Wait, NASA, you said that gases move randomly in all directions. Is that true?
How high is the ozone layer?
According to your paradigm, I believe it's like as high as a little bit higher than an airplane goes, like 10 miles or something. But regardless of that, does gas
6 to
particles move
30
randomly in all
miles.
directions? Does gas particles move randomly in all directions, or do they go down only?
Move in all directions.
Here we go. You're going to misunderstand acceleration. Go for it.
If they move randomly in all directions, then you can't claim that gravity's only holding them down.
Oh, for fuck's sake!
What's the difference between velocity and acceleration, Angel?
Velocity is has directionality to it. Acceleration is just actually I don't know the difference.
Yeah, I don't know the difference between
does have
velocity
a
and
vector.
acceleration.
Velocity is speed in a direction, and acceleration isn't.
Yes, it is. Acceleration has a direction.
Okay,
If I
so do
throw a
gas
ball
particles
into
move
the
randomly?
air, if I throw a ball into the air, the moment it leaves my hand, the velocity is up, the acceleration is down.
Okay, so do gas particles move randomly in all directions, or they're held down by gravity?
Let's go right back to this
Both.
thing. I don't understand. You don't understand acceleration.
Don't
though, but we're
understand.
talking about
I'll
gas
keep going
particles.
on my script. Should I stick to my script as well?
Wait, so when you fart, Roohif, does it go down or does it disperse in all directions?
It goes in all directions. The velocity is in
not
all
down.
directions. The velocity is in all directions. The acceleration is down.
Why do you hate me
Okay.
so much, Roohif? Why do you keep getting angry at me, buddy?
I'm not
Because
angry
you're
at you. I'm pointing out to everyone that you are
Why do you call me
disingenuous
names
and
Why do
incredibly
you call me names?
stupid.
Roohif,
Why do you
is there
call me
such a
names
thing as
then?
deceleration? And with this, where do you apply
No,
deceleration?
not really.
Yeah,
Not
okay, so
really.
you're
It's,
just
it's,
using
it's a
acceleration.
magnitude.
Gotcha.
It
Yeah,
has a
just checking.
magnitude in the
Yeah.
opposite direction. Yeah.
Hey, Roohif. So, does gas particles always seek vacuums?
Gas
Like
particles
if I
don't
have
seek anything. They just respond to whatever forces they're under.
so if I have a vacuum chamber, okay, and I have another, it's attached to another chamber via a valve. One has gas, one doesn't.
How big are these? How big are these now? Are these 5 liters now? So you can
It
compare
doesn't
another.
matter. What?
Are you
Yeah,
compare, it
5
doesn't
liters.
matter, right? It doesn't matter. We're going
5
to compare a
liters. Let me
small little vacuum chamber to the entire universe now. Right, got it.
Yeah. Right. Which is the stronger vacuum? Which is the stronger vacuum? A
Vacuums don't
5-liter
have a
little
strength.
vacuum. Okay, so a vacuum, the 10 to the minus 17 tall vacuum. Okay.
Vacuums don't suck.
No, but you do.
Your mama does, that's for sure. I got it right here, right now.
Come on, bro. Come on, man. Come on now.
What you do? So if I open the valve, does the gas rush into the vacuum?
Yes, because all the molecules are going in all different directions at very high speed. Yes.
Right, and you've seen the pale blue dot image, correct?
Probably.
Okay, so
Pale blue
the
dot or
Earth
the
is
blue marble?
the Earth, pale blue dot. So the Earth is literally
Pale
a
blue
little
dot's
speck
like a
of dust in
dot.
an infinite.
Yeah.
Yeah, the Earth is a little tiny infinitesimal dot in an infinite space vacuum, correct?
Sure.
How come the air hasn't seeked equilibrium then? Like you
Gravity.
just said it would.
Because
Gravity.
Because they're retarded.
Right. Let's say there's a molecule that all the air goes in all different directions, right? And there's one molecule that's going up at 500 meters per second. Right? Gravity still affects that molecule.
Why is it going up?
It slows down.
Oh, it slows down.
Yes.
At what point?
It's
At what
mass.
Because of temperature.
At what point does it slow down? At what point does that molecule that's moving up slow down and go back to the Earth?
Yeah, you can apply Newton's laws to it. I mean, in
experiment-
reality, though, it'll
experiment?
most likely hit another molecule and bounce off.
That still doesn't
So the
negate the
definition-
fact of how pressure works.
Yeah, the definition of gas pressure is the amount of force exerted by the molecules on the walls of the container. Do you agree?
I don't agree with that.
Then you deny science. Welcome science deniers.
Okay,
So you deny all the gas laws, Roohif.
No, I don't deny the gas laws.
So what's the V for volume in the gas laws then?
What's your container? What are you applying it to? You're doing like PV equals
How do you-
nRT? Is
so
that
how
what
do
you're
you-
doing?
So wait. How do you have a volume of gas without a container? Are you claiming that is gravity a container
You
for gas?
don't need. I can draw 1 cubic meter of air in my room with my fingers.
Yep.
But that is a volume.
Right. Can you?
That's not necessarily
Okay.
mentioned.
So,
You're in your room though.
hang on a second. So is gravity a container for gas?
You can call it that, yes. It keeps
Can you bring me
the
5
gas-
liters? Can you bring me 5 liters of helium without a container using gravity? Please?
You know, the
because
over under on
it will be
the over-under-
displaced.
real
It will
quick.
be
The over
displaced.
under. Hold on, real quick. The over under on Roohif calling someone champ is 6 minutes.
Oh, no. Angel's way beyond champ. Way beyond.
Oh yeah, yeah. But again, you said gravity is a container for gas. Can you bring me helium 5 liters without a container using gravity, please?
You know what's going to. Well, hopefully you know what's going to happen. The helium.
So
Why
if you
does
know what,
helium
so
go up?
the answer is no. Then, so is gravity a container for gas? Yes or no?
Yes.
So can you bring me 5 liters of helium without a container using gravity, please?
No. It's not the same
Why?
question.
So can you bring me 5 liters of sulfur hexafluoride without a container using gravity, please?
A 3-sided or a container.
Three-sided. 3-sided. So wait. Is that a 3-sided?
5-sided. 5-sided container.
Oh man.
And even then, some will
This is
escape.
so funny. This is so funny, dude. Come on, Roohif. Why aren't you a flat earther?
The thing is, he's invoking like size, right? Like scalability. Like if you go smaller, then you don't need a container. Is kind of what it sounds like to me. But rather your size, man. The container has to be there. The walls have to be there for gas, anyway.
Sulfur hexafluoride. It's one of the most dense.
Hey,
gases.
Roohif, so hang on a second. How do you recreate a vacuum without a container, Roohif?
Can you do that outside? No.
Oh, you can't. So then, is the vacuum of space contained then, seeing as that's the only way to have a vacuum in the first place?
I would go to space.
You would go to Narnia?
Oh. You're
Roohif, just answer my question. You just, it's the only way to have a vacuum with a container to sustain it, yes or no?
On the Earth, yes.
Oh, okay. So then, you don't have evidence that the vacuum of space can exist without a container there. Scientifically,
I don't need to invoke a container. I don't need to invoke a container.
You can just invoke magic.
You
not
have
magic.
to if you invoke pressure.
What?
You have to.
Why?
It's the antecedent. You're just being disingenuous. You're answering the question with the bias, and you're trying
parroting
to
Oakley.
push. I don't give a fuck who I'm parroting. I'm parroting fucking laws of fucking science and physics, bro. Like, if you want to disingenuously avoid those laws of physics and science, then go ahead. By all means, do what you gotta do. But if you want to speak truthfully and you know, and honestly, you're gonna have to invoke this law that we understand very clearly. We know
Okay, what is
how
the
it works.
purpose of a container? What is the purpose of this container? Okay, so there'll be like molecules of gas hitting the container and bouncing off, right?
Yep.
That's what it does. Okay. So when we go super duper high, there's no fucking pressure. So there's no molecules hitting this imaginary container.
Whoa. Did you just say there's no pressure? You know that's impossible, right?
Well, technically,
you know there's no pressure.
Yes.
Okay, so if there's one molecule hitting the top of a container, is it still gas pressure, Roohif?
We have gas pressure without a container. It doesn't. You're not saying that it hits a container.
You're assuming that. You're assuming that.
So
we have gas pressure. Even Roohif, 10 to the minus 17 torr is positive pressure. You know that, right?
Yes.
Okay, so if
It's
we have
basically
positive
zero, though,
pressure,
right?
so if we have positive pressure still, even one molecule, like you mentioned earlier, hitting a container, then that would create pressure, correct?
Yeah, any molecule moving would have pressure. Yes.
All right, welcome to flat
Any shape.
It's not about the shape of the earth at this point.
Disingenuous fuck.
It's not the shape of the earth.
Unbelievable.
I'm wondering, how about being disingenuous when you agree with me?
It's not even.
It's just you cannot have an argument with faith.
We're not even talking about the shape of the earth, Roohif. We're talking about science.
Did you not disagree?
Talking about the shape.
Did you not disagree with me?
Well, we do kind of realize we do observe, you know, these faster moving molecules in that ionosphere up high, you know, from I don't know if you guys realize that, but I think it's due to us getting closer and closer to that container. You know, the conductivity gets a lot higher up there. Doesn't mean it's negative towards the 17, but it does mean things are accelerating, it seems like.
Hey, Roohif, so if you duck behind a hill, do I see you?
And I was mentioning ionization. That's kind of what I was referring to.
You know what? Even with that, even within that, you still are speaking about a gradient that can only exist with the container, because the second you release that container, if you cut off the top of that container, you will not have a pressure gradient, because the laws of gas are going to obviously disperse to fill the void.
If there's a downward force, the gravitation, the gas laws do not have a downward bias that gravity provides.
Right, exactly. I agree. So then if gases move randomly in all directions, gravity's not holding them down. I agree. Thank you.
Exactly.
Oh, you've had a reset already. You've had a reset already.
You proved that.
Velocity
goes right back to the same old bullshit.
The velocity is in all directions. The acceleration is down.
All right. If you, Globy's in. If you duck behind a hill, do I see you?
Globy. Who's Globy?
You're Globy, right?
Oh no, I thought you said. I thought you meant Globy McGlobe.
No, Globy. No, like Globy's in the room, right? If you duck behind a hill, do I see you?
No.
So if something's behind the curvature of the Earth, do you see it?
Oh,
nope.
Jesus Christ. Do I need to post?
Answer, guys. It's a simple answer, Roohif. It's a simple answer. Just stop being disingenuous. It's a simple answer. It's a no.
Thanks.
It's funny how this guy.
Let's have a flat earther tell us not to be disingenuous. This is irony.
It's funny how Roohif claims that I'm disingenuous, but he can't answer a simple question. If something's behind the curvature of the Earth, Roohif, do you see it?
Okay, I've posted the Black Swan meme showing there is clearly some
I'm not
atmospheric
talking
effect
about
that we
black swan.
need to. Okay, but we're
I'm not
talking
talking
about
about black
refraction.
swan. I'm just saying, if you just said if you go behind a hill, I don't see you. If something's behind the curvature of the Earth, do you see it?
Depends how much light's built.
So is the Chicago skyline? Do we have line of sight to that actual skyline?
My
Is it a
God.
straight?
the
You mean
Chicago
straight line of sight
skyline.
or curved line of sight?
A straight line of sight to the building. Do we have direct line of sight to the buildings?
You see the bottom of the buildings or only the
We
top?
actually do.
You guys are retarded,
I think
bro.
we
You
do
guys are
have
stupid.
straight line of sight to the.
Why
to the
do we only
tops
see
of the
that
building.
on certain days of the year? We should see it all the
Wait.
time.
As
Wait, hang on a
smart
How
as
come
second.
we
you
never
are,
see the
but you
bottoms? How
find
come we only
yourself
see
so
the tops
stupid.
of those buildings?
So Roohif
That's
just said we have direct line of sight to it. Do I
To the
have direct
top.
line of sight to you when? Yeah. So when you're behind the hill, do I have direct line of sight to you?
Well, depends on how much light is curving. If I'm just behind a
Depends.
hill, yeah,
It depends. Like if you go
yeah.
behind a hill, do I have direct line of sight to you?
It depends how much light's curving. If I'm like 10 centimeters below a very, very shallow hill 20 miles away,
Don't say
maybe
it.
you
yeah.
can.
Don't say it. Rick. Don't say
But
it. Don't say it.
the
So wait a minute,
calculations
you can
don't
Wait.
see them.
Don't
So
say
if
it.
you can
Rick.
see them, you want to know why if you can see them, you shouldn't be able to see them. Got it. That's
the
really great.
calculations
Don't say it,
the
Rick. Don't.
calculations
So if I can
Roohif,
see him, I shouldn't be able to see him because I can see him.
Roohif,
What?
the
So wait. If I play
calculations
peekaboo, if you play peekaboo with me behind a hill, do I see you?
Whatever you'd like me to say, I'll say it. So yes, right?
Yeah. Oh. Okay. So when children play hide and seek, do they have to take refraction into account?
Do they play hide and seek over the course of miles or in the backyard?
If they did play in like hill piles or whatever you just said, then yeah, would they have to take refraction into account?
Is the curved path of light substantially different to a straight line?
If it was, do they have to take refraction into account?
If it was, then yes.
So snipers can
Oh
hit the
no.
enemy that's hidden behind a wall. Got it. You're lost, bro. You're brick.
Hey, I got a question. Hey, at what point did you realize the Earth was flat, Roohif? Like, really, no bullshit. Like, at what point?
Yeah. When you say no bullshit and then talk bullshit, that makes me respect you less. Sorry.
Oh, come
There's the guy
on,
who says
man.
we can see behind a
Just
hill,
level with
but
this,
you
bro.
think we
Just
can?
level with it. Just level.
Dude, but you just said we could see behind a hill. How are we talking bullshit?
It depends how much light's curving. Right? And you know what
Wow,
you're
Rudy.
doing. Like, you're such a disingenuous
Roohif.
Says the guy who thinks when going behind a hill I can see you still, dude. Who's being disingenuous here?
Depends how much light is curving. Yes.
Ruhif, you just said kids playing hide and seek would have to adjust for refraction. Who's being disingenuous here?
Yeah, if they're
Seriously,
playing over several miles where the curvature of light is
Wow.
substantially different to a straight line.
Oh my god.
Roohif,
But I'm disingenuous, right?
Roohif,
Yes.
let me ask you a question.
All right.
Mathematically. Is refraction calculated on the height of the object?
What does that mean?
Is refraction calculated off the height of an object?
I have no idea what that means. It's like
Okay.
purple, smell yellow.
I do. The
Let me
answer is
help you
yes,
out.
Roohif.
Let me help you out. If you have an object in the distance, is refraction in the formula? Okay? Is it calculated by the height of the object? Yes or no?
If I'm taking an angle to an object of known elevation, can I work out what the refraction must be?
Is
that
refraction on the height of the object? Yes or no?
No,
I
it
don't
is
know what the question
combined
means.
with the height of the object, the temperature and pressure, and distance to the object. You've got to include the distance of the object.
Okay. Now, okay. You're right. Distance is also involved, but isn't it also the height? Yes or no? It's a very simple
Yes.
question.
Also, it
Okay.
is included.
Okay,
Hey, APOC,
so now,
hold on. Can you fix your mic, APOC? It's real muffled.
And by
Can you explain what he means?
and by
What does he mean?
I think by height, he's talking about the millibar pressure.
Okay.
Yeah,
no,
why would distance increase the
close.
density of the atmosphere? Why would that happen?
Pay attention closely, okay? Pay attention closely, guys, okay? It's really simple. Is height involved in the formula for refraction? Yes or no?
Well, the pressure, which is a function of height, typically, yes.
They can't answer it, Jay. They just can't answer.
Oh my God. Okay, so if
Such a disingenuous fuck, Angel. We're trying to clarify the question.
Wow.
Man,
Unbelievable.
So disingenuous.
Okay, let me put it this way. Let me put it this way, okay? If there's an object at a distance, am I calculating the refraction to its height or no? Yes or no?
I don't know what it means.
That's an ill-formed question.
Oh my God.
No, it's not. It makes
In the
perfect
formula
sense, dude.
is height. Okay. Oh my God. In the formula is height a factor for refraction? Yes or fucking no?
Elevation above sea level? Yes.
Okay.
Which is
height,
represented by the pressure.
Okay.
Yes.
Okay. Which is height, right? It's height, right?
Well, sometimes you high pressure at low altitudes, or vice versa. Yes.
Okay. Wait, no. Okay, the answer is yes, right? God damn, it's like pulling fucking teeth here. Okay, with that being said, okay, now Roohif, you're a fucking mathematician. Mathematically, can you calculate something times 0? Yes or no?
Equals 0?
Can you calculate something times 0? Yes or no?
Yes, it equals 0.
Okay, so when we are seeing the surface of an object, okay, that's at a distance, this refraction value is based upon the height of it. But if you now try to calculate the surface of it, that surface, that baseline, is a 0. Yes or no?
Oh God.
What?
Oh,
Are you saying there's no refraction at sea level? Like, what are you trying to say?
No, did I say that? It's a very simple question. What I'm trying to get at with you, Roof,
No one can understand your question, Brock.
Pay attention.
No.
Pay attention.
It's simple. It's simple. Just because something is at a 0 elevation does not mean it's at a 0 millibar pressure. And the 0 millibar pressure is what we're using, and that is often equated with height. And so, 0 sea level is 1013 millibar, not 0.
So then this is where I'm trying to direct you so you understand mathematically. If you're going to ascribe a refracted value, it's only going to be based upon the height, the top of it. No. You can't say no. That's absolutely correct.
Yes, I can say
and
no.
Let me tell you why. Okay, because
I'll tell you why. Because it's no.
Shut up. Let me finish. When you ascribe a calculation to it, you're going to base it. Let me put a human to this formula. Okay, you're going to go off the top of their head mathematically, because that's where refraction is in the formula. It's going to be basing upon that position of the object in a distance. Now, if you go to the feet, right, the foot of that human standing on this fucking surface, you are now calculating it to a 0 value. This is why you can't calculate refraction to their feet. This is why you're going to only calculate it to their head, because technically.
Okay, let's take that.
What are you talking about?
I'm not done.
Okay, let's take that. So we have the pressure at his head of, say, 1010 millibar, and the pressure at his feet at 10,008 millibar. Okay, we're still going to use 10,008 millibar. We're not going to use 0.
You're ascribing temperature and pressure to a physical location, which is not the fucking thing in the formula. You are not ascribing, when you have height squared minus distance squared divided by height times the square, or height squared for its refracted value. Hold on. I know the formula, bro. The refracted value equals height squared minus distance squared divided by height squared. So if you think that you can just like nonchalantly invoke a 0 value because we're talking about the surface. No, yes, mathematically.
Okay, let's work with that. No, let's work with that. Okay, so at your height of your eye, you're at, say, 406 feet. At your feet, you're 403 feet or 402 feet. You never
but it's
0.
a 0 value. It's a 0 value.
No, it's 402.
No, it's 0 because that's the baseline that you've created. So okay, let's go over water. Let's go over water. Okay, if you have an oil rig that's 50 feet in the air, the refracted value is based upon the top of the oil rig, not the bottom. Mathematically, this is why I love fucking bringing this up to you guys, because I love to fucking hit you with your own fucking paradigm.